everyone. Is this mic really necessary? It's actually good? Okay, I'll leave it. That's good, that's good. All right, so I guess hey Andy, how's it going? So I guess we'll get started. So this is the MapReduce hands-on. So by hands-on, it's a little bit hard to offer an actual hands-on because that would involve you installing software that is probably not going to work the first time, and we only have a little over an hour together. So for the first half of this, I will be doing basically a tiny lecture on the backstory of Hadoop and MapReduce, how it works, and so on. And then for the second half, we'll have a few exercises of writing MapReduce programs. So this won't be teaching you how to use the command line, which is what some of these hands-on deal with, but rather the art of writing programs in a way that, using the MapReduce framework, which is easy but a little tricky to learn the first time you look at it. Okay, and feel free to shout out or talk however you like during the presentation if you have any questions. So my name is Mike Cafarella. I'm a professor in the computer science department here, and I use MapReduce quite a lot for my own research, both as a tool for conducting research, and also I've published on optimizations and modifications you can make to MapReduce systems to make them more efficient. I've also been deeply involved in implementations of MapReduce through the Hadoop project, although I'm not working on Hadoop anymore. I did a lot in the early days. Okay, so let's get started. So what people usually call Hadoop or MapReduce is actually based in two systems, the Google file system and Google's MapReduce. Search engines, primarily Google and others, were the first to really address a lot of the large-scale data-centric problems that people are facing these days. And although they went first in terms, their problems involved things like processing search logs and processing web crawls, they weren't the last. So the kinds of problems that you see here, some of them were encountered by search engines, meaning things like analyzing who was saying what on the web is something that's certainly a problem that Google would want to address. But things like bioinformatics, meaning doing sequence alignment for genetic research, for example, these kinds of database matching problems that I've mentioned here at the bottom, some of these might mean a lot to you and some of these might mean absolutely nothing to you. The idea of these, though, is that a lot of time people will have large structured data sets that they'd like to combine, and although there are tools in the traditional relational database world for doing that, they're often very difficult to use and expensive for one reason or another. And by using MapReduce and the distributed file system that accompanies it, you can avoid a lot of the traditional problems associated with combining large data sets. So we'll get to these applications by the end. But my point here is just to illustrate that although this file system and programming technique arose from search engine and web processing needs, their current application extends far beyond that. Okay. Oftentimes, the solutions that the search engines came up with were pretty ad hoc, but Google was the first with these papers to create a more general framework. All right, so it's worthwhile to think about why they would have done this. So let's imagine that you're Google in, say, 2002, and you're trying to index the whole web. Why didn't they just go buy a bunch of Oracle instances and then try to fire them up and get their web crawl done? Well, so let's say the web is about 100 billion pages large, and you want to have, say, 1 week freshness. That means every page on the web has to be indexed roughly once a week. Now, some of that stuff you can do less frequently than once a week. Some you have to do much more frequently than once a week. Say you're looking at the CNN.com homepage. But let's just say we want it once a week, typically speaking. That means we have about 10,000 minutes to burn, or rather 10 million pages every minute. If we imagine that a disk that you can go buy at Best Buy, the best one you can purchase at Best Buy is probably going to give you about 100 megabytes per second. If you spend more, you can maybe push that to 120 or 130 megabytes per second. And the average page takes you about 25K. So that means we're looking at processing about 24,000 pages a minute. In other words, we need about 417 parallel disks just to read the data, let alone actually process any of this stuff. So we're already looking at what would be, in a traditional database deployment, an absolutely massive system. And also, we don't want to pay the costs that a lot of the traditional database people are doing. So this is getting to be a large problem. And if you imagine we wanted to do this in a day or even an hour, then the numbers become even a little bit more startling. So Google's and the other search engine provider solution was to use very large clusters of machines, machine set sizes that previously had only been seen in supercomputer style deployments, not in distributed database deployments, which were generally on the order of, say, 4 to 16 machines. Instead of having these very large few machines that were traditional in data management before this time, we're going to have very large sets of machines that all have their own local disks and a rich network to connect them. And the point is our problems are much, much larger than traditional relational database ones. So in the distributed programming case, your databases, traditional database style applications are a lot about reads and writes to data, say managing a bank's transaction query load. But we're going to need a large number of CPUs. So a lot of this is fairly expensive data processing rather than just keeping track of which bits have changed. When you get to this many CPUs that we have to manage, the programming challenge becomes really difficult. Even if you could express your program over all these machines, you can't actually know when you're writing your program which machines are going to be up at any one time. So when you have this many machines, some are always down, some are going to go down during the processing of your job. When you think that these jobs are going to be lasting for hours or days rather than the traditional seconds or even less than a second in a transactional database case, then being able to survive the failure of machines or exploit machines that come into the cluster is a really important property. That's the long-lasting property I just mentioned. So even though machines die and some machines depart for maybe administrative reasons, the job has to survive. And this is really, from kind of a computer science point of view, the novel intellectual component of MapReduce, that people had not really thought about data processing jobs. They thought about robustness in that your data should not become incorrect when the machine dies, but they hadn't thought about a query or a processing task that could last so long that you had to survive the partial failure of your set of machines. Finally, a lot of these programs that you want to do, like text indexing, genetic sequence alignment, image processing, these are near impossible to express using SQL. Okay, so let's talk about what we'll actually talk about today. I've just gone through the introduction. I'll talk a little bit about background. I don't know if anyone has tried to run a MapReduce program before. If you have, anyone? Okay, a couple people, that's good. So most of this will be novel to most people here. I'll talk a little bit about the kind of machine assumptions that go into the file system and MapReduce frameworks, and then talk a little bit about the Google file system. There's a Hadoop equivalent called the Hadoop distributed file system. They're almost exactly the same. Then finally, when I get to MapReduce, I'll talk about both the background of how MapReduce works, and then we'll go through some exercises. But first, let's dive into the background here. Okay, so when we're talking about data this large, even just storing it is a big challenge. So the files are usually much larger than we can have on a local disk. I've talked about why relational databases are unsatisfactory for various reasons. Sometimes people will use a shared NFS filer like a NetApp device or an EMC device. These are not only very expensive per gigabyte, but also have properties that you may not want. If you have lots of CPUs constantly reading data, then it's not so great to have all your data somewhere else. It would be nice to have the data locally attached to where it was being processed. So the file system here is an effort to support the kind of large scan style reads that we want to support for these large data sets, but also do so at a price that's manageable for both hardware and the administrative costs that go into it. If you've ever had the misfortune of purchasing a NetApp or even EMC device, then you know that the price you pay at Best Buy for a gigabyte is much, much less than the price you're going to pay per gigabyte for one of these machines. One of the real virtues of the Google File System, or HDFS, is that it gives you some reasonable amount of data storage at a much lower price than any of these other systems. Okay, so let's talk for a minute about the machine assumption. So you can run the file system in MapReduce on your local machine. In fact, you should download it and run it just on your tiny little local CPU and your local disk, learn how to program and so on. But if that's what you do, you're not really exploiting it. A lot of the code and a lot of the work that went into these systems is designed to exploit these very large collections of machines. So when people talk about the cluster, what they're talking about is a big room full of stacks of machines. It looks a little bit like this. So here we have various racks full of machines. A rack is a big stack of servers, maybe say 40 of them in a given rack. This is a machine room that supplies electricity, cooling, and other services to all the machines. But the point here is that these are very large and expensive compared to your PC, but not very expensive compared to, say, supercomputer-style deployments, where your program is going to run. So the whole point is that your data storage and your program are executed across these large families of machines. At any one time, the system knows where bits of your computation are, but you don't have to. Okay. So, sort of the atom of the data center, or of the cluster, is something we'll call the rack. The rack is just a shelf full of machines, but it has a few properties. Okay, it's not quite as easy as filling it full of machines and then going to bed. There's a few things to remember about the rack and the cluster. So here's the basic vocabulary. The administrators and people who are buying this stuff have to know more than this, but you don't if you're a user. So servers go into a rack. Each server has local processing and disks. These machines are not exotic. They are just, they can be as simple as horizontal versions of your desktop PC. In fact, I run a cluster of actual tower-style machines because the cases were cheaper. These don't have to be fancy machines at all. All the servers in a rack generally share a network switch. The only reason that that's important is that network connectivity among machines in a rack, because they share a switch, is going to be free or very cheap and easy to get. Connectivity between racks is going to be comparatively expensive. So MapReduce and GFS are both designed to avoid transferring data across racks if at all possible. Now, you want to do some amount of transfer across racks because you want these to work in concert, and if one rack gets hit by a meteor, you want the other rack to survive. But in general, the systems are designed to minimize use of the scarce resource of inter-rack connectivity. Okay, so now you can forget everything else you know about data centers. All right, now let's talk about the file system. So the distributed file system is what actually writes your data to disk. Google and a lot of the modern applications have very strange requirements, and the design they came up with was equally strange. So one is that they want this to be as cheap as possible, so the file system should survive high component failure rates. We're going to buy the cheapest disks we can, run them hot, and not care too much if an individual disk dies. That doesn't seem like the best way to run your data, and maybe you don't want your bank balance to be stored that way. But for the data set sizes that we're talking about, we can survive these failures. Instead of a traditional file system that might have a very large number of tiny files, say the file system that runs on your laptop, we're going to have a modest number of very huge files. So let's say a few million, and these are going, this slide is a little bit out of date. 100 megabytes or larger, it's probably way bigger than 100 megabytes. Even multi-petabyte files are not unheard of. The idea is that it looks to you like a file, but the actual bytes on disk could be stored across many disks and many computers at any one time, even though that fact is totally transparent to you. Moreover, files are a little bit strange in that they are usually append only. So if you are editing a Word document, then you might change one byte, one character in the middle of the document and leave the rest unchanged. The kind of files we have here are generally not like that. If you think about the logs that your web server is generating or the readings that your instrument in the lab is throwing off, generally these spit out data and never revisit the data that it once spit out. So if you have data of that type, I would say traditional databases where I'm twiddling your bank account to go up or down $100 is also unlike that. We have files that keep growing bigger and bigger, and we rarely go back and edit bytes once they've been written to disk. And then finally, we usually want to do these large streaming reads. So we want to start at the top of our web crawl, read the whole thing, process all the entries in the web access log, read your genetic sequence just once. We don't have any exotic jumping around requirements on these disks. Okay. Oh, that's someone outside, okay. And then finally, because these jobs are big, we usually favor throughput over latency. If we can do the entire web crawl in an hour, we don't actually care what happens in the first 5 minutes. And you can see this frustratingly when you download Hadoop for the first time, because you will run what seems like a very simple job, and it will take an unbelievable amount of startup time, and you'll think, this is really bad. There's no way it's ever going to process all my data. Don't lose hope. It's the startup time for a lot of these jobs that takes a while. And in your actual deployment, the parallelism of the cluster will eventually give you good performance in the end. Yeah? Yeah.
So you said it's append only. Does Google actually not throw out archival versions of pages?
So it's not, they tend to be append only. The Google file system will support actual modifications to the data, although if you do that a lot, the performance will be bad. I don't know whether Google throws out the archives or not, but you can imagine a world where I run the web crawl once a day, and the file's append only, but the files are called December 1st webcrawl.txt or something like that, right, where I throw out yesterday's web crawl. So throwing stuff away may or may not be consistent with the model here. But this is a good point in that the file system that you view looks an awful lot like the hierarchical file system you're accustomed to, for both good and for ill. That means it's easy to understand, but it also means that there's a management problem that you will probably face in your own work, in that you have to figure out the file name should be in a directory where everyone can find it for a certain day. Whatever habits you've become accustomed to in naming files on your own disk, now your group has to agree to those standards so that everyone knows where to find certain files. It's not like in a traditional relational database where there's some amount of metadata that's being tracked along with each file. There are new projects in the whole open source Hadoop universe that try to address that, something called hcatalog, but they're very rudimentary right now. Okay, so here's what they come up with. So files are stored as a series of what they call chunks. This has some resemblance to what a traditional file system does, but the size of a chunk is enormous. The original paper said 64 megabytes, but in fact most systems today are configured for chunk sizes much larger than that, say 128 or even 256 megabytes at a time. This just means there's a region of bytes of size 64, 128, et cetera, that lives at a certain place on some disk in the system. Reliability is achieved through replication. So for every one of those chunks, it will appear, say, 3 different times across the cluster. So machine 1 will have a copy, machine 22 will have a copy, machine 99 will have a copy. And if any of those machines become inaccessible because the disk goes bad, or the network card blows up, or someone turns off the power on that rack, then there's still copies of your data available. So unless you become supremely unlucky, your data should be able to survive the failure of a component at various levels, right? Whether it's a fine-grained component on a disk or even an entire rack. And then finally, there's a single master node that coordinates access to these chunks and also the metadata. So there's a single node that tracks a mapping between the name of a file in that hierarchy and the chunks all across the cluster that makes it up. So somewhere there's a table that says file webcrawl.txt consists of, say, 100 chunks, and those chunks are called, chunk 1, chunk 2, et cetera. And then I also have a map that's constructed in real time of where those chunks exist on the cluster. So when a reader wants access to, say, crawl.txt, it goes and asks the central node, please tell me where the chunks are, and then I will go fetch them in order. Okay. If you're familiar with POSIX, this is the traditional, say, file system interface that your software would use. This is not that kind of a file system. If you want to use the Google or Hadoop file system, you have to write your software specially for it. That said, you should never do that. There are all sorts of tools in place so that you never have to actually look at that API. Okay. So here's kind of a quick review. These chunks, because they're append only, or they're generally append only, we usually don't have to revisit them. They can be copied and replicated pretty easily. a series of pieces of software called chunk servers actually hold and serve the chunks. So when a client wants to read a certain region of bytes, it will ask the master for the location of a chunk that would be appropriate, then we'll contact the chunk independently and say, please give me the following region of bytes, and those bytes will be transmitted over the network to the client. The master holds this metadata that I talked about, both the file name to chunk list mapping and the chunk to location mapping. And the client contacts the master for metadata first, and then the individual chunk clusters, chunk servers, excuse me. Okay, so here's a very kind of quick diagrammatic view of what's happening. You can see in the upper left-hand corner, there's a box that's meant to indicate the application with a sub-box called the GFS client. This just means that whatever software is running, whether it's on your machine or inside of MapReduce, which we'll get to in a minute, that software has a small piece of code that's specifically designed for GFS. The thin lines here indicate metadata transfers. So the top line, which is labeled file name and chunk index, it goes from the application to this box called GFS master. That is, the client is asking, please give me some metadata. It responds with this line called chunk handle and chunk locations, which is telling it where in the entire cluster can I find the data that I'm interested in. Then the GFS client contacts that machine, gives the handle and the byte range that he's interested in, and then you can see this very fat, dark black line indicates a data flow. The chunk server responds with genuine bytes that the client wants. So this means this system is very poorly designed if you're going to read 1 byte every 500 megabytes, right? It means you're going to have to contact a new machine for every byte you want to obtain. But if you're in this business of doing these long sweeping reads, then the overhead is pretty reasonable. You contact a machine, what you get back is a stream of however big your chunk is, or no larger than however big your chunk is. Okay, so here's the fancy animated version. You can imagine here we have a master, a small cluster of 6 machines, and a client in the bottom left. We ask for the file name info, get back the metadata. I contact the machines in sequence and then get the data back. There's another twist when it comes to writing, which is interesting to know about, just so that you feel secure that your data is safe, but you don't have to know this as a user. When you are writing data, it gets copied as you write to multiple machines. So those 3 replicas that I talked about, those are built as you're creating the data, and in fact, it won't successfully close the file until the system is sure that it has 3 replicas. So you can be sure that as soon as the data actually closes, there's some amount of safety associated with it. Okay. So here we have to think about what happens if, so we have some safety built in, but what happens if the chunk server dies, if the master dies, network switches and so on. There's constantly metadata being exchanged among all of these machines to basically asking each other if they're still alive, if they can still talk to each other. And importantly, the master can ask the chunk servers to make extra copies. So if a rack of machines go down, they stop sending the heartbeat message back to the master. The master will know because these following machines are no longer reporting in, the following chunks have now disappeared from view, and thus the replica count has gone from 3 to 2, which means we're starting to go into the danger zone. It can then ask the surviving members of that, or the surviving copies of those chunks, to copy themselves somewhere new so that we can get back into the 3 replica area. Finally, you may be wondering about that master. This has been a matter of some contention. In this version, in the original published version of the MapReduce work, there's something called the shadow master, which is always creating a live replica of the master, but cannot actually enable novel files to be created. It's true that if the master is destroyed, then the whole file system is destroyed, so you should be cautious about your master. That's probably where you actually do want a relatively expensive disk. But there has also been work on making a truly distributed master node so that any one of the masters could die and the whole system can still provide service.
So a system like Google, though, isn't that also a huge throughput bottleneck?
The metadata actually is pretty light, right? So if I want to read 64 or 128 gigabytes, the number of bytes I exchange with the master is basically the name of the machine I go to find it, right? So the master only has to handle a few bytes to me. So it's true that at some point, maybe there's a workload that would swamp the master, but you can go surprisingly far without hitting that. It's the actual data stream, which is sort of the hard work, never goes via the master. Okay, so this is a small illustration of failure, which is mainly here to show off my PowerPoint chops. So you can see that we have, again, 6 members of the cluster, and they've been labeled with the chunks that they might have. So for example, chunk server 0 has chunk 33 and 95. So this is the only time that in your life that you can actually use this animation in PowerPoint. Let's say that chunk server 4 dies, goes down the wormhole. So now 90 has disappeared. So the replica count for 90 has gone down. The master recognizes that that machine's heartbeat has disappeared. And after a few seconds, we'll ask chunk server 5, please make a new copy of 90 so that we have safety for 90. And then finally, we achieve like the level of safety that we want. Choosing the right level of replication is a little bit tricky. If you are only running, say, a 6-node cluster, which is not unheard of in kind of your initial research style deployment, then I'd say you're probably okay. Then you're paying you're cutting your disk usage by a third if you have 3 replicas. For so few machines, I'd say you're probably okay with 2. Depends on your personal comfort with this. I run my 8-node, or rather 5-node cluster at replica 2 because I don't want to actually waste that much data. If this is the thing that's going to get your Nobel Prize, maybe you want 3 replicas. That's up to you. Large clusters, you almost certainly want 3. Okay, so here are the things to actually remember about the Google file system or the HDFS file system. If you remember these things, then you can live your MapReduce life pretty successfully and forget the rest. Okay, files are large. That's important. This means whatever file you have, there's no file system around that's better able to handle it, at least, size-wise. Files are stored in a file system style hierarchy, not a database, which means, again, there's a management burden that you have to carry. Clients have to be custom written to use this file system, but you shouldn't do that. So one of the clients of this system is MapReduce. So MapReduce will read and write things, and when you write your MapReduce program, you don't have to think about the direct file system interface. There's also a command line tool that provides simple operations like file copy, move, rename, and delete. All the basic file system operations you need. All that's been implemented, and they use the direct to file system interface, but there's no need for you to do that. There are internal safety. They spend a lot of time actually guaranteeing safety of your data, which is good because the file's so big, there's nowhere to copy it. Having more replicas is the best way to back up your disk, unless you have a spare data center and you can actually copy it across data centers. There are only a handful of institutions that are able to do that. Basically, this is great for, well, huge files because it's your only choice. Or work product. So if you have a large data processing stream where you have some input A, process it a certain way B, and go to versions B, C, and D, if this is part of your daily work, then this is almost certainly where you want to store it. But it's a terrible choice for the things you are accustomed to putting on file systems. So if you think you're going to save money on an NFS filer by storing all your code or your personal files on this, don't do it. It's more trouble than it's worth. You could do it, but it's a bad pick. The performance will be bad. You won't save that much money, and so on. I've mentioned this, but it's actually very important that everyone is now looking at your own file system. Everyone's sharing a disk now. The disk, admittedly, could be petabytes big, but you're still sharing that disk. So there are things like groups and group permissions in place in the file system. But whoever you do research with have to agree on your practices. Okay, so now let's get to the fun stuff, which is what we're going to do with all this data once it's on the disk. So writing the programs here is quite tricky. We have the problem that the data is huge. Even if we could suck it down the network on our local laptop, that's still going to be pretty horrible. It's going to take a long time for your laptop to finish the job. And we have the problem that if we want to run on a cluster, the machines are still blinking in and out all the time. So even if you could figure out a great way of expressing your program in a distributed way, then the very fact that one machine is going to go down, another machine might come up, is going to really increase the burden on you to get your custom distributed software written. I remember when in about 2004 or so, I was at that point working on an open source search engine, and we had just spent about 4 or 5 months getting the distributed version of our text indexer working. So we had a large web crawl. It worked great as long as you could do it on one machine, but then we spent a lot of time doing this distributed indexer. We were quite proud of it. I think about 3 hours later, we saw that the MapReduce paper had come out. We realized that in fact we had to chuck all this work because MapReduce was a much better way of doing it. Because the thing that took at least half of our time getting the safety regarding machine failures and so on, we could get for free by just running it on top of MapReduce. Okay, so the things it provides are near automatic parallelization of your code. So as long as you write to this framework, it will execute it on multiple machines simultaneously and will even pick the number of machines that's best for you. So based on conditions in the cluster at that point, how many machines are available, what other tasks are being run, and so on, it will help you to get your job done as fast as it can. It has fault tolerance so that if a machine dies, your program can survive. And then there's some nice software tools associated with Hadoop. So you can have a little web interface that says what the status of your job is, how close you are to completion. And this programming interface is quite nice. Finding people, MapReduce, I read an article recently that people who know MapReduce and Hadoop are getting something like a 10% premium in salaries in Silicon Valley and so on. Whether that's true or not, people who can write in MapReduce are a lot easier to find than people who can write a fantastic distributed piece of software for you. So even as just an abstraction for writing the software, ignoring the other benefits, it's still very useful. You might not be able to squeeze out as much efficiency as you can from a custom-made solution, but the programming model is so simple that a much larger class of programmers can actually be productive with it. Okay, so here's the basic model. So it may stun you to learn that MapReduce programs are written using a map and reduce function. And here's the whole thing in a nutshell. So map is a function that takes a parameter, which is a pair called key comma value, and it transforms that into 0 or more pairs of a different key value pair. So here you'll note the key prime and value prime. That key value prime or key prime and value prime don't have to have any correlation to the inputs. You could write a map function that takes in pairs of, say, let's call it URL comma web page if you have a web crawl, and it could emit a random string and then a random integer. There's nothing stopping you from having a ridiculous map function that does whatever it wants when emitting these pairs. You probably shouldn't do that because there's a point in giving it input, otherwise you won't have a useful program, but there's nothing about the MapReduce semantics that require that output be reasonable. The reduce function receives, so we generate this intermediate data from the map function, that key prime and value prime. The reduce function is invoked once for every unique key prime in your entire run. So we run the map function as many times as needed over your entire input. You can imagine that if we're in the case of a web crawl where we have a key being a URL and a value being a web page, then we will invoke map once for every time we see that web page in your input file. Reduce is invoked once for every unique key in the intermediate data. So the map functions could emit multiple pairs with the same key prime value. In fact, they often do in most applications. the system will collate or all of the values that share a key prime and will invoke reduce once for those. It will pass as the second parameter all of the values associated with that key prime. So instead of a single key value pair, here the input to a reduce function is a key value and a list of, or a key and a list of values. Finally, it emits 0 or more pairs, and those pairs actually go to disk. So here is a dead easy example of word count. So we're going to imagine that the system is trying to process an input file, just a text file, and we want to figure out how many words are actually in the file. Now that seems like a ridiculous example, but if the input text file is the web, then this is actually a pretty challenging task. The point here is that we want to look at the text and emit a file which has one entry for every unique word we've ever seen, along with a count of how many times that word was seen. So we expect the, of, and to have enormous numbers, and anti-disestablishmentarianism, or whatever crazy word you want to pick, should have a relatively low number in the resulting word count. For English on the web, we'll probably see on the order of 15 million entries, or however many unique words there are. Okay. So here's what it looks like. This is a little bit of pseudocode. It's inspired by the Hadoop MapReduce interface, but I've obscured a few things to make it more readable. You can see at the top, this is near Java. So you can see at the top, the map function is receiving 3 inputs. Something called a key, which you can imagine is a long in this case, or just an integer value. It's called long writable for sort of internal Hadoop reasons. A value, which is of type text, and then an object called output. The type is too awful to actually put on the screen, but the point is that this is an administrative style object. The system is giving your function a handle to it, and we'll see how it's used. So imagine that if I have a text file, then how do I transform a text file into a set of these pair inputs to the map function? Well, the key will be just the number of the line that I'm on, and the value will be the contents of that line. So the first line, anything before the first new line will have 1 associated with it, then that text, then 2, the text, and so on. If we have an enormous file, then the key could be, say, 10 billion, right, if it's the 10 billionth line in the file. So here's what the actual code does. In the top half of this, we basically do initialization. We create something called word, figure out something called line, which is just the string version of whatever the input was. And then we create a tokenizer. And the point here is the tokenizer is just going to break the line at white space boundaries for us. Then I'll move, so this is easier read. We have a while loop that asks the tokenizer to iterate through all the tokens in the input line. That is, break it into white space and give it to me one at a time. And then I will set this word object, which I created above, to the value that the tokenizer gives me. And then finally, I'm going to tell the output object, emit a tuple, or emit a pair, where the key is word, and the value is the integer 1. So for every word in the input line, I'm going to emit a pair that has that word and then the number 1. So this is going to be a very kind of boring output from the map function. Now let's look at reduce. The idea here, you can see in the top, we've got a key of type text. So the key values here don't have the same type necessarily as the inputs to map. We've got something of type text as the key, and then a values object, which is multiple integers. Right? And then finally, we have a similar output object. And this is dead easy. We create an integer called sum, which is initialized to 0. We iterate over all the values. We sum the values that we get. And then finally, we output something key as this value key is the key. So it has the same key that was passed to reduce as the output. And then we pass the sum that we've totaled. So for every unique word, we sum up all the ones that we got, and then we output that to the disk. So here's a data-centric view of it. We might have a set of text here on the left-hand side. When we undergo the map transformation, it yields this intermediate data that you see on the right. So we've got a series of pairs in whatever crazy order it wants. For the case of a single map invocation, it will emit this in the order that the data was processed by the map. So yes appears as the first object emitted because yes is the first item in the text and so on. It undergoes the so-called shuffle phase, which we'll get to in a minute. And in the reduce process, we collate all the values that are associated with a single key, undergo reduce, and then we have the following output on the right. So it's still in the form of these pairs, but we've now summed up the counts for every unique token that we've seen in the text. This is what actually gets put on disk. So the output format of your MapReduce job has to be in the form of these key value pairs. Now most tasks can survive this, but if you are doing, say, like text generation, then you have to be a little bit clever of how you encode it. You might have to your key value for text generation might be, the key is the unique identifier for the paragraph you're generating, and the value would be the actual content of the text. If you are doing, say, image processing, then you can imagine the key is just some metadata that identifies the image, and the value can be the bytes that make up the image. So here we are calling key value things that look like traditional programming variables because it's easy to fit on the board or on the screen. But when you're writing your software, you can be very expansive about your definition of what makes up a value. A value could in fact be a tree of different objects in certain cases, if that's what your program demands. Okay, so let's talk about the actual execution pipeline that MapReduce is carrying out. So the system has 3 different stages. Map and reduce, which we know about, and then shuffle, which goes in the middle. In stage 1, you've written your map function. The system's job is to run that map function in parallel as much as it can. So it will go to the cluster, figure out what machines are available, also figure out where your data is stored across the cluster, because remember that we've got the stuff on the distributed file system, and we're going to co-locate processing with file system storage. And we're going to run as many map tasks in parallel as we can. Because a map task is defined as just this pair, and your input presumably has a large number of these pairs, then the processing of line 1 of the text really has nothing to do with the processing of line 3 in the text. Whether that happens on one machine or say 10 different machines, one for every line in the text, the semantics of the problem is irrelevant, or your choice about where to run the map function is irrelevant to the semantics of your output, right? You can have a correct output in either case. In the second stage, shuffle, this one you don't have any influence over. The system will do that collation and sorting step that I talked about. So it will look at all the maps that have ever run across the entire cluster, and will have sort of a large multi-machine swap of data such that all the places where the word "the" showed up get sorted and sent to a single target machine. We'll get to that in the next step. That target machine is where the reduce will be run. So in this step, we take all the data that was generated by the shuffle stage in sorted order and process it with reduce. So for the number of maps that get run is dependent. You can give hints to the system, but it's really dependent on properties of the cluster at the time that you run it. The semantics of your program are totally irrelevant to the number of maps that are run. That's not true of reduce. For reduce, the number of reducers that you run will be the number of output files that your program generates. So depending on what program you're writing, you might be able to survive with, say, 100 reducers, which means a lot of work can happen in parallel, or maybe you need to generate just a single file. If that's true, then you need to have just one reducer, and the opportunity for parallelism is much reduced. So when you write your software, you can tell the system how many mappers you would like to have, but you have to tell the system how many reducers you will have, because the output of reduce will actually get sent to disk. Now, the inputs to reduce, unlike map, are guaranteed to be in whatever order is imposed by the keys. So in the case of words gotten from this text, they'll be in alphanumeric order. Integers will obviously have their own order. Your key could be an exotic object that you define where the order is going to be unique to your application. So there's support for generating complex objects where as long as you can supply a function that compares in two instances and tells you what the ordering is, then it will guarantee that order in the sort. Okay, and finally the reduce is whatever reduce emits, or the output is whatever reduce emits. So if we go through the processing, the client tells the MapReduce master, I'd like to run the following job. In this, I'm calling it a grep job, which means I'd like to find lines of the input that match certain criteria. And when I submit a job, I'm telling it what code to run and also what input files to run it on. So the code is just a pointer to something I've compiled. The input file is one or more paths in that GFS, HDFS file system. The master then contacts all the machines in the pool that are free at the moment and says, please, here's a copy of the code that I was just submitted. Gear up and run on a region of the following file. The system will figure out what region of that input file everyone should run on. And it will try to run processing where the bytes are actually located. So ideally, it will not have to transfer any bytes over the network to actually get the processing done. It can just read it from the local disk. That may not be possible in all cases. You can imagine that for whatever reason, for a given chunk of data, all the replicas of that chunk might be busily processing other MapReduce jobs. And so the system can't actually guarantee local processing, but in the vast majority of cases for clusters that are not super heavily loaded, which is almost all of them, it does a very good job at minimizing network traffic. In the shuffle stage, all these worker nodes are going to exchange outputs. So they will figure out, I want all of the instances of Parrot to show up on machine 4. So that means wherever the map functions were executed, anytime Parrot showed up, I have to transmit those to machine 4. Wherever examples of the word Google showed up, I have to go transmit that to machine 6. The system handles that swapping routine. And then finally, the master asks it to start the reduce phase. That runs, and then the job completes. Okay. The inputs are all on the shared file system, and so are the outputs. That intermediate data exists in an interstitial kind of MapReduce-only world. You can never actually see it, but MapReduce is making decisions about where to store that data at any one time to try to increase its ability to survive partial machine failures. So if a mapper dies halfway through, we restart the mapper because again, the processing of one line is somewhat irrelevant to the processing of another line of your output, of your input. And so if a machine dies partway through processing, we'll just pretend it never happened and kick off another one. Now, that works great unless you have non-deterministic map functions. If you have a map function that depends on the time of day or on random numbers, then you can get strange semantics from this re-execution. If you ideally, your map function is idempotent, but if it's not true, then that may or may not be acceptable to your application. So the system doesn't guarantee that the output will be exactly the same from a second rerun of a map function, but it will guarantee that you get the same inputs. So as long as you are strictly relying on the inputs to generate the output of a map, you should be A-OK. Okay, so there are also, as I mentioned, there are all sorts of rules here for robustness. If a machine dies with a relational database, they just restart it. It's not going to take that long, so it's not so bad. That's not so hot if you are deep into the processing of your job. So for a map worker, we can just restart the thing. For a reduce worker, we cache the inputs from map functions. So we don't have to restart all the way to the inputs. The map intermediate output is stored on disk and can be reused in certain cases. Okay. So this whole framework, which is great for distributed programming and for surviving failure, also gives you a few other nice features. So you can imagine there's a problem of these slow but not quite dead machines. So your machine might have a misconfiguration, like let's say the cache is turned off, or let's say that that machine has mistakenly 1/10 of the DRAM chips that it should have. It really, if it were dead, then we wouldn't have any problem. But if it's alive, then we think it's working. It's just not working well enough. In this case, because a map function can be executed multiple times without ill effects, we can run multiple simultaneously and kill the second place or third place finishers. So if we think there are machine-dependent problems, we'll just start lots of copies, and whoever wins the race is the one whose output we'll actually use. I mentioned the thing about data placement. For the case of word count, that intermediate data might seem really inefficient, because in a typical text, even a short one, you'll emit a pair for every unique instance of the. That seems like a big waste. There's an extra function you can provide called the combiner, which will essentially do a local reduce after map execution on the machine before it's transmitted to all the others. So in some applications, reduce is not really needed. In a lot of applications, you can dramatically reduce the amount of work that the system does by providing a good combiner. Okay, so the number of this seems like a pretty simple model, and also seemed a little bit tailored to text, at least for given the examples we've seen. But the applications that people have managed to solve using MapReduce are just astonishing. So it may not be surprising that we can do log processing and sort of web graph processing very well. Other web style applications like inverted index construction, that is building the stuff that actually supports very rapid queries when you go to google.com, or sorting enormous files can be done with this. There used to be something called the TeraSort benchmark, which was how fast you could sort a terabyte of data. That's been obsoleted because various MapReduce clusters solved it so fast it wasn't fun anymore. So they've modified the benchmark, but that was a benchmark for many years that MapReduce has now tackled. People are doing massive scale image conversion with this. So I know there are, the New York Times used it to transform the image format of all of its archives into something that would be more easily used on the web. This was one of the first high-profile uses of the Amazon version of MapReduce, which is really just Hadoop with a couple tweaks to work on their infrastructure. But I've heard of other applications as well that are much larger than this, where people are trying to do computationally intensive transformations of a bitmap that comes in. Okay, so now let's start with an actual part of the tutorial part. This is we'll talk about log processing or log filtering. This is a very typical application. For web companies, they look at their server logs quite a lot. They'd like to know what are the most popular search queries. But for anyone who has a website, which is almost any company these days, you have a very interesting log to go look at. It figures out, it's a record of what people have done at your site. A log doesn't just have to be web accesses, although that's a very popular one. It could also be, say, a transaction log of who bought what at your store that day, and so on. So here's a typical snippet of a log from a web server. It looks like a little bit of garbage right now, but let's break it up a little bit. So I've highlighted in red the different regions of each line of text. The first one is the IP address where the web request came from. The second one is the timestamp where it happened. The third one is whether it was a read or a write to the web server, the HTTP method. The next one is the URL that was used, the version of the protocol that was used, and then whether it was successful and how many bytes were transferred. So this seems like a pretty techy, not very interesting application to many, but in fact you can derive a lot of interesting information from this. Things like what time of day are most popular for your service, so that you could figure out, should I buy new machines? When should I run my backup system? What URLs are most popular? A lot of content sites like news organizations use this to figure out what they should assign their reporters to go do. This is how you can figure out things like the top 10 hot articles on NewYorkTimes.com and so on. All sorts of pretty interesting data can be derived from even these really basic information that we get from an interaction with the user. Okay, so your mission is to use MapReduce to count all the URLs that had a result code of 200, indicating success. So we want a MapReduce program that's going to process our logs, which could be enormous if we are a very popular website, and figure out the most popular URLs that actually were successful. So here's the template. This is a great exam question. I've given you a hint as to what the interface for MapReducing should be. So you might take a moment, and so this is where the hands-on quality comes in. Take a moment and sort of write with text or on your iPad or just even in your head what the content of map and reduce might be. Obviously, we're not checking for syntax because we don't have 30 compilers running, but figure out a little bit what the content of these functions should be. I'll give you about a minute, and then we'll talk about the answer. You can even ask questions during this part if you'd like. Yeah?
So is the implication of what you were talking about something like Google search itself?
Yeah.
How Google gives all of its details.
Yeah.
Is that it's not actually inverting the contents, that it's simply sort of reprocessing the raw data on every search?
No, no. One of the applications that they said was an explicit motivation for MapReduce was to generate that inverted index. So MapReduce jobs are these very high latency things that are almost never in the actual interactive stream. Meaning, like, you go to Google, they're using the byproduct of a MapReduce program. They're not executing one on demand for you.
Okay, so they're using MapReduce to invert the
Yeah, that's right.
index and then do a normal search of that inverted index to solve it in a query.
That's exactly right, yeah.
But I guess the corollary for a data set that's changing very often, which you would think would apply to them, and wasn't necessarily the size of the web,
Yeah.
you could actually use this to avoid creating that inverted index, right? And use it dynamically or not?
It depends on what your responsiveness requirements are. There will be, if you need, you can imagine the products that my company sells are changing all the time, right? I mean, Walmart has however many terminals going all the time. But it's okay if the data that comes out of it is a little bit out of date. I mean, if it's an hour late, then I'm fine with it. But if this is, you can imagine whatever time-critical application would not be suitable for that. The extreme of this the extremely bad version of this would be these high-frequency trading things that people do, where you want responsiveness in, say, 20 milliseconds rather than, the tens of thousands of milliseconds that you'll get with this one. Okay, is there a brave soul who wants to talk about what they would put in the map function? Not so brave. It's not that bad. Okay. What's that? Yeah. Yeah, that's you've got it in a nutshell. So the map function's simple. Let's imagine, through the magic of pseudocode, that we've parsed the line into these component parts, right? So we have fields 1, 2, 3, etc. I test if field 6 is equal to 200, and if so, then I emit the data. I emit field 5 with a count of 1. So the fifth field here is the URL. And if it's not equal to 200, then I could emit 0, or I could just do nothing. So it's always okay for me to emit 0 results from a map function. And the reduce function is exactly the same as before. I'm just taking strings, collating them, and computing counts. So this one is really dead easy. It's a near word count. I'm just doing a test on the content before actually emitting the count. In a relational database world, this would be a selection or something that you would handle using the where clause of your SQL query. You can implement the equivalent here in your map function. There are some systems that you may have heard of, like Pig and Hive, which give you a SQL-style interface, but actually run MapReduce programs. So you can write something that looks like a SQL program, but is executed on a very large file, and that will get compiled into a MapReduce program that actually executes on your code. In fact, people who have used MapReduce for a long time, for simple things like log processing, they usually find that the queries you can express using these systems, Pig and Hive, are more manageable over the long term than these custom Java programs. If you're doing this for research needs, then your map and reduce functions may or may not be expressible using these other systems. But if so, I'd encourage you to look at them. Okay, so there's a bunch of details that I've breezed over in explaining all this. So, for example, how does the file translate into these key value pairs? I mean, there's nothing obvious that like with a text file, you'd have an integer 1 that describes the line number. That seems a little bit strange in some ways. How do you indicate the input-output file? How many tasks do you use? This is terrible. We talked about that. How do you even kick off the job? In Hadoop, the answer to all these questions is the job.conf object. I've breezed over how you actually start up the job. The three most important components are going to be your map function, your reduce function, and then this region of code that tries to answer all of these questions. So you can, some of these are easy, or they're just setting a parameter, as in the case of how many instances of reduce should be run. Others, like how you translate a raw stream of bytes into a series of these pairs, you have to not only tell, you have to tell job.conf the name of the function that you would like in order to do that. So Hadoop has built in a number of basic and popular record breakers that will take, say, a text file and translate it into a key value pair at every new line, or whatever file format you're talking about. For most known file formats, even some ones that you might think of as a fairly niche concern, there is available code to do that, so you might check online. If you're doing a totally eccentric file format, you may have to write your own function to do that translation. It's this grab bag of miscellaneous configuration parameters, as I said, and there's a very nice tutorial on the Hadoop website that will go through the word count example and tell you what that job.conf should probably look like for you. So there's plenty of documentation on that online. Okay, now let's have a more exotic example. Okay, here we now have two files. We've got the same log file as before, but now let's imagine we've tired of the academic life, and we're now taking our website and turning it into a commercial concern. And we've got a second file, which is the ad rates associated with showing each of these URLs. So here, I've got the logs, and then I've got a totally separate file, which is just the posting of how much money I earn every time someone goes to one of these URLs. And the mission here is use this ad rate data file to figure out how much I earned today from the weblog. So I have a record of who saw what from coming to my website, and I have a record of how much I can charge for ads on each of those URLs. You know, one is about my academic paper, so it gets a penny. Another one is about asbestos lawyers, so it gets 10 bucks. The things are different. Excuse me, let me crouch down here. And an important thing, let's assume that a key value pair that comes to map can be drawn from either of these files. So when you indicate the input to your program, you can indicate more than one file. You'll just say it comes from Apache log.txt, and it also comes from adrate.txt. So your map function could have quite diverse inputs. However, it will always come in the form of a key value pair. Yeah?
So in that case, would the source file be part of the value? You store a tuple with the value in it?
Well, that's kind of up to you. I'll leave that to you for figuring out, and then we'll talk about possible solutions. So here's, again, the template that I'll provide to you. I'll give you a hint, which is that I've changed the format of it slightly. So the type of value is now going to be text rather than the count that I talked about earlier. This is one possible way of solving it. There are actually lots of fine ways of solving this one. But again, I'll give you about 30 or 60 seconds to think about this and how you might generate the answer. And I'll get my head out of the way. All right, is there anyone who, again, wants to volunteer an answer? Well, you had at least a start of it. Do you want to talk about it a little bit?
I haven't been able to go a lot further.
Okay. Yeah.
So, I mean, so are you just taking the URL as the key, and then you could pull the value of that particular URL in your mapper
Yeah.
as the value, and then you pass that to reduce?
When you say pull, what does that mean exactly?
I don't know, you said you could specify the key value pair from any of the files, right? So,
Yeah. Okay, so I think,
So you have some statement in there, if the I don't know, if the key is equal to this, then the value is equal to.
right, okay, so I think you're on the right track. So here's one solution. So let's imagine that in the earlier part of the program, I do some parsing of each line, and I can tell which file it came from, right? Or I could encode it in the key. But the important thing is that when it comes time to emitting the values, I do so conditionally, right? The key of my intermediate output is always the URL that I'm talking about. That part's critical. If that weren't true, then the reduced part's not going to work. So no matter what source I'm talking about, the URL always has to be my output key. But the value that I output along with that key will be conditional on my input and will either be a count or a cost, right? Okay, and I'm going to include a little bit of poor man's metadata here by associating in text the label of what it came from. That's a pretty sloppy way of doing it. I don't actually recommend that, but it's nice for teaching's sake. In the reduce function, I have keys and values. Remember, the key is always going to be a URL, and the values is going to be a mix of things. It can, in some cases, for a given URL, it will be something drawn from the log. In some cases, it will be a price drawn from the add rate file. I iterate through all these values, and if it's in the count case, then I increment my count. If it's in the cost case, then I will assign something to the cost value. I'll assume for now that every URL only shows up once in that cost file. But if the add rate file had other information like time of day or something like that, you can imagine enhancing this program to account for that. And then finally, I'll emit a piece of code which is just the product of how many times I saw it and the cost that I derived from the add rate file. So putting this up, we're already starting to slightly abuse MapReduce. It doesn't express these kinds of multi-file things really effectively. That said, it's something you have to do all the time. So there are a handful of solutions. One is to do something like this, where you conditionally do work based on the input, or on the source of the input. A second one is that if that second file, like add rate, is small enough, then you can load it into RAM for your map function. So there is a specialized function you can override that will be started. So a map function is started on a machine. It processes an entire chunk of data. You can have a function that fires once at the start of that process. So once per 64 gigabyte chunk, let's say. During that phase, you could load a file from disk into RAM, as long as it's small enough to process for the entire thing. In this case, add rates may actually be small enough, depending on your website and so on. So that's the second option. Your third and best option is to let something like Pig or Hive handle it for you. So this kind of somewhat kludgy maneuver is basically encoded inside the Pig and Hive processors, and will allow you to express these things, which in a database sense would be called a join. Yeah?
So are ifs expensive? And more broadly, is there a profiler? So if you do this, you can find out you did it wrong without like a stopwatch.
An if statement, is it expensive?
Yeah.
There's nothing about this if that makes it any different from an if running in a compiled Java program.
So the answer could be yes.
Well,
but it depends, right?
I mean, if it's, if p equals np or whatever, I mean, it depends on what the Boolean is that you're testing, right? The vast majority of ifs are pretty cheap.
Right, but is there a profiler that will tell you where in your code, you're spending your time.
You know, as of, I don't know the latest and greatest on this. The admin tool gives you a little bit of information, but probably not enough. As of a couple years ago, the answer to that was no. But I know there has been some work on it, so I'm reluctant to say what the state of the art is. Some of my students have worked on stuff like that.
So this may be a naive question, but you put the logic in the map function, but could you run two map functions and have logic in the reduce function and then do sort of a join?
So the join here, the fact that I'm taking a URL from source A and a URL from source B and using that as my join key, I'm relying on the sort procedure to do that. So shuffle is the thing that is finding the URLs from different locations and putting them together. And the reason for that is, or the reason I have to do that is that a map function is not going, again, aside from the case when file 2 is so small you can fit into RAM, an individual invocation of map is not necessarily going to know about all of the relevant URLs, right? You could have lots of things going on in parallel. There has to be kind of a post facto way for them to communicate. In a traditional distributed relational database, that kind of communication happens much more efficiently than it does here. So MapReduce is not great for doing these joins, but it's so good for other things that we end up having to do it, and you kind of live with the bad consequences. Okay, so we're nearing the end of, in fact, we're pretty much at the end of my prepared remarks. So I mentioned that MapReduce can do all sorts of different tasks. There's some of these it handles great. Some of them, it's not perfect for it, like in this join case, but it is a really good lowest common denominator tool. So it's relatively easy to learn. It does a not terrible job at almost everything, and a pretty good job at a lot of things. So people have found it to be a very handy instrument for whatever they're working on. There's one particular use case that might be relevant to a lot of people, which has sort of evolved over the last couple of years, which is people have struggled for a long time with doing data warehouse style analysis of all their structured data. They might have large databases which are interesting and they want to ask questions of it, but getting to the point where you can actually ask interesting questions is really burdensome. A lot of that comes from the fact that you have to design schemas in a traditional relational database right at the start. But oftentimes you don't know what questions you're going to ask until you've looked at the data a lot. And so people are evolving toward a use case that you might describe as schema at query time, where you collect your data and put it in as, you collect all the bytes you'd ever want and put it in HDFS, which is about as cheap as reliable storage can get. And then when it comes time for you to actually run your analysis, you run a small MapReduce program that extracts just the fields that you're interested in. So in the case of a weblog, who knows what crazy questions we're going to ask of the weblog? You know, here we wanted to know what the most popular URLs are. Maybe in the future we want to know, find bugs in our web app code by looking at which URLs give non-200 style results. That's a question that we may not have anticipated when we stored the data. And in a relational database, the traditional data warehouse setting, you'd be out of luck at that point. By deferring those decisions till later and having the infrastructure that makes it cheap enough to do so, then you can have a much more flexible kind of data mining and analysis platform. Okay, so we only have a couple minutes to lunch. There are these birds of a feather talks that I was asked to mention, meaning there's lunch boxes, I guess, that you bring, and then there'll be tables that have sort of themes to them. If you have any questions now, or I'll be able to stay for lunch for a little bit, then I'm happy to answer them. So thanks very much. Yeah?
You mentioned learning is relatively easy. What are the best sources to learn on?
So there's a short tutorial on the Hadoop site itself. There's a series of videos that were created as part of an effort by Cloudera, which is sort of the Red Hat of Hadoop. And these videos are great. You can find those online. And then finally, there's a pretty high quality O'Reilly book about it that's effective and cheap.
You mentioned earlier that
Yeah.
Are there good heuristics for teasing apart what are going to be the good use cases and the not so good?
To the extent that you have these straight shot processing tasks, it's great. If you have to do 9 joins in a row, then it's not so hot. That said, there are some things like PageRank, which are essentially 50 joins in a row, and PageRank is a popular target for this, largely because for a long time there was no better game in town. Now there's a system you may have heard called Pragle, which came out a couple of years from Google, which is specifically for graph-style computations. So in that case, people identified one use case that you could do with MapReduce, but was not ideal, and they've come up with a tailored application. My guess as to the next big target of that would be machine learning algorithms, where people have implemented machine learning algorithms on top of Hadoop. There's a package called Mahout, which is used for this, but you could do a lot better with a custom solution. So I think Mahout's great, but it's worth looking into other things too. Okay, thanks everyone. Hi.
I do not have a slide, but I will attest.
The new
I have no, it's actually big. Yeah, and part of it's NIH, but it's also in the standard practice guide. So when we give a lecture at the medical school, we have to stand up and say what our potential conflicts are. So I'll be doing that.
Why would that be?
Why? Well, it's part of it is related to the whole conflicts of interest policy at the National Institutes of Health and the need for disclosure. Like, for example, I forgot to fill out my forms that I'm getting $965,000 from drug companies last year to push drugs. Okay. Hey, it's great that people are still hanging on for the last part of the cyber infrastructure days. It's been a great, I think it's been an absolutely great event all along. Hats off to Dan and Catherine and everybody. Sharon, it's been wonderful. This session is related to personalized medicine and healthcare. And what we're going to do is give a comprehensive assessment of where we are as an institution and try to frame that in terms of where the country and the world is going with this. And, you know, so we'll take an inside look, a deep inside look, and we'll go outside and look and see how, you know, at the boundaries we can increase the kind of engagement that we want to have happen to make the experience of healthcare personal, more personal than it is right now. And I should say that you know, listen, I mean, we do a pretty good job at this already. It isn't like we don't treat the patients as individual. They have something called the individual patient care experience. We heard more about that last night when our strategic plan for the health system was unveiled by Dr. Peskovitz at the dinner at the Michigan League. And, you know, but there's something big going on regarding personalized health. There's a convergence of things. And so let me plug in my notebook and introduce our panel more formally. And I will say this right up front, that I do have some engagements with scientific boards. I chair the scientific board of Apistry Corporation, which is a company that does cloud computing in several spaces, including the life sciences. I chair the board for not-for-profit scientific technical board for One Mind for Research, which is a neuroscience, not public-private partnership on the East Coast. And I work on the scientific board of Ascentia Biopharmaceuticals, which is a holding company that has 6 biotech and pharma companies within it. And I have no conflicts of interest with any of the things that I'm going to tell you on those things. So that's, Catherine, the kind of things that we have to do now. And that's coming from the institution and the NIH. Now, is that happening on campus too, guys? I mean, are folks having Marios? Are you having to declare your potential conflicts before you talk? It's coming your way. This is NIH has really been the kind of driver on this. Okay, good. Now, we have really a nice panel put together. And I'm going to limit my time. People have heard me talk for years. And Andrew Rosenberg, who is Associate Professor of Anesthesiology, and very importantly, our Chief Medical Information Officer of our health system, and has incredible responsibility for shepherding the process, which he will describe to you in some detail, of re-engineering our electronic health record system. And you're going to hear a lot about that. And what I will do is make a few brief kind of framing remarks and turn it over to Andrew, and he'll give a talk that he and I and Jocelyn DeWitt, our Health Hospitals and Health Centers CIO, and Ted Hans, CIO of the hospital, worked on together and was presented as our strategic vision for the health system information technology, and was actually derivatized into a set of priorities and budgetary allocations to actually make our plan a reality across the three missions of research, education, and patient care. And so Andrew will be taking the bulk of the time here today to tell you about that, followed by Professor Larry Ahn, who is with the Department of Internal Medicine and the Comprehensive Cancer Center and the School of Public Health. And he is our expert on engaging patients and populations and individuals and making the healthcare and medical and healthcare experience more personal. And so what I will do is start and turn it over to Andrew and just describe all the things we're doing in our health system now, framing against the national landscape, which has really changed a lot. A couple years ago, there was something called the HITECH Act. I think how many people have heard of the HITECH Act?
I'll describe.
Andrew, that's his assignment. He'll tell you about that. But that mandated certain things that we had to do in terms of implementing electronic health record systems in our inpatient and ambulatory and frankly in the physician's office, and making the United States of America a place where we have electronic health records that are used meaningfully. And that's the law. And that was put into effect in the HITECH Act as part of the ARA bill that went through Congress a few years back. And so there are incentives to get people to play, but ultimately in 2015, there will be penalties if you don't. And so we're moving towards a tipping point now where in the United States of America, we'll be going digital here in the next few years. And that's needed. Okay, so, already got some issues. I hope it's not going to be big. Okay, it looks better. It was coming up weird on my screen. So that's just us, okay? And we really want to have some question and answers and discussions. We're here to share information with you and to learn from you. This is just the scope of where we are. I think it's important just to set the context. The University of Michigan is a basic biomedical science powerhouse. We are now, actually today, we have the fourth most funding from the National Institutes of Health of any academic medical center in the United States. We bring in some $360 million from NIH in funding for our research. Much of it is basic research, okay? There's the basic research, which is fundamental discoveries, and then there's clinical research, which is, checking things out in the hospital, in the ambulatory care clinics, out into the homes, doing clinical trials, testing hypotheses. The vision that we have for our health system and frankly the country is to move some of the basic research through clinical and translate that out into practice. That's our dream. And our dream is in some ways enabled, but also made more complicated by the emergence of measurements like bioinformatics or things like that are coming on board real quickly. So the bench to the bedside, out into practice. That's the kind of flow. And we want to see a flow back and forth. So when Larry talks about engaging the community, he's talking about being out there and testing things that are going back and forth. Maybe it's research, but maybe it's actually, delivering the appropriate clinical support and clinical care to our patients. How do we personalize that? So that's the overall scope. And so the University of Michigan views itself as a special place where we have all this basic research going on, and special places like the Cancer Center and the Depression Center and the Aging Institute and all this kind of stuff. And then, you know, in clinical research, and then ultimately engagement with the community, both locally and nationally. And we have the CTSA is one of the big programs that we have that's funded by the NIH to help us with that, the Clinical and Translational Sciences Award. This is a slide that shows a picture, basically, of some of the new ways to think about research. And it's relating the molecular measurements to something that you see in the physiology. So, you know, the relationships between the genes and what happens to you in your organ. You know, do you have a gene or a set of genes for a Mendelian trait or a more complex trait that predisposes you, say, to cardiovascular disease or coronary artery disease or something like that? And so, you know, in the past, you know, we would kind of measure what we call the phenotype, but now we have the ability to kind of do modeling and make measurements from bioinformatics and kind of relate the two. And you know, sometimes even we can add more information in between. We can look at genetics and perturbations of genetics, and then look at, you know, how that turns into proteins and metabolites and relates to the physiology, cellular physiology, and, you know, relates ultimately to a condition. And then we could look at things like environmental practices, smoking, nutrition, things like that. Genotype to phenotype. You know, a lot of basic science here, but a lot of now basic science done in the clinical departments and in the practices, you know, as we try to understand this better. You know, and you're thinking about it a little deeper, and you'll see this in Andrew's talk. I think you'll see it again. You know, and I think some of you saw Gonçalo Abacassis' talk and Jim Cavicoli yesterday. You know, the world of bioinformatics, where we're measuring the whole genome of individuals. Or, you know, the most exciting thing that I heard yesterday from Gonçalo was that his paper in Nature of the 1,000 Genome Projects, and he shared with us, you know, and they've analyzed 374 of the 1,000 genomes for that publication. It's the most highly cited publication of any biomedical research publication in the world came out of this place this last year, the 1,000 Genomes Project. So back in 2001, the genome was sequenced at the low, low price of about $3 billion. And now we're looking at $2,000 per genome. And Gonçalo, you know, mentioned yesterday in his talk that he hopes in the next couple of years we'll be analyzing 20,000 human genomes. Here, on site at the University of Michigan, is ramping up to our DNA BioLibrary program, where we're anticipating taking 100,000 specimens, keeping the DNA, and linking in the data from the electronic health record, and Andrew will describe that to you. So, you know, there's all kinds of measurements right up the stack. One of the strategic planks of our health system research strategic plan is getting more involved in metabolomic studies and obesity. I think we all know that's a big problem in this country and in the world, you know, but it's nature and nurture, huh? It's not just what we can find out from, you know, the bioinformatics. There's lifestyle issues. I think Larry is going to deal with some of this kind of stuff. So going from the genotype right straight up to the phenotype. The organ, that heart that we saw, the tissues within the organ, like in the kidney, different tissues, and so on. It's all right there. And so, you know, one of the things is, and I've only got 2 slides, I'm going to turn it right over to Andrew, is clinical decision support. One of the big 3, going fully electronic in the electronic health record, getting clinical decision support to work just right, and increasing the fidelity and the usability of the interfaces that give us access to the information. These are kind of the big 3 issues that are on the, you know, big horizon for clinical and health informatics. And, you know, the simple idea here is, gee, you can only keep track of about 5 ideas in your head at once. So what happens when we have all these other measurements coming up? You need a computer. Whether it's to code the bill with the ICD codes, you need a computer. Whether it's to make a decision based on measurements that are being making in the lab, you need a computer. You need information management. You need to put it all together that way at enterprise scale. And so just my last slide is to show you, well, I had a nice talk with this wonderful fellow, Gianrico Farrugia, MD, at the Mayo Clinic in Rochester, and here's his plan, a $350 million 5-year plan to implement personalized medicine at the Mayo Clinic. These are the topic areas. Clinomics. Well, remember that stack? He made up a new word to describe that whole stack I just showed you. They call it clinomics over there at Mayo, just so you know. Epigenomics. It's not just the genes, but it's modifying those genes or even the proteins that are involved with those genes. And actually, there's some kind of heritability that goes on with that as well. And we have to keep track of it. Pharmacogenomics. Big subject. You know, for example, in our psychiatric clinics, we can make measurements of how people metabolize certain, say, SSRI compounds, antidepressants, because some people really metabolize them, some people don't metabolize them so well. So if you're going to treat, if you could measure individually, you can increase the treatment effectiveness. The microbiome. It's kind of like the talk we saw this morning about the ocean floor. We have 1 trillion cells that make up our body, but we have 100 trillion microbes that make up our body. 100 times more microbes are in your body as cells than the cells we have in our body. You know, and the microbes that are here, you know, kind of in the little nape of the elbow, are different than in here. And actually, the microbes that are in between each and every one of your teeth are different and have been, we're starting to measure all that right now. And it's one of the big areas of medicine and infectious disease. And biomarkers. Gee, if we really want to understand how somebody personally kind of presents themselves against this molecular way of thinking, we can make a measurement, and oftentimes that measurement is called a biomarker. So that's Mayo's plan. We're implementing something very similar to here. I'm turning it over to Andrew so he can tell you what we're doing. And thank you.
This is working out good, so I can move around. Well, as we're getting set up, thanks, Larry, and thanks, Brian. My name is Andrew Rosenberg. I'm as Brian said, I'm the Chief Medical Information Officer for the health system, and that's actually a relatively new position. We've had a CMIO of the hospital, but not really of the health system, and one of the reasons why that's important is the reason why you're here. The reach out to a variety of other areas now is really like no other, and living in a silo of just clinical care or academic research care is very passé, and cyber infrastructure, like many things, is really a foundational tool that simply, those kinds of outreaches are not capable without this kind of work and this kind of infrastructure as well. I also need to apologize that I'm in my scrubs. I was in the OR briefly this morning. Normally I would not be in my scrubs for something like this, but I just simply didn't have time to change before I came here. We're in the hospital, that's never an issue, but I apologize for that. So I am going to hopefully this clicker work, because I tend to like to walk around while I talk, but we'll see, and if it doesn't, no problem. I am going to go through a variety of, an overview of the lay of the land from an informatics point of view, but as much lay of the land from the health care and the trends in healthcare right now, because I think that to understand what we're trying to do, you need to understand several of the problems. So what I will be discussing is actually this very small portion of what we now like to call the Athey-Puck diagram, as he and Frank Mannion and others helped put this together. But we're talking about an enormously complex, multi-$100 million informatics infrastructure system on the clinical side now. And that's just one very small part of a much, much broader and much more complex system. Fundamental to clinical, operational hospital informatics versus academic informatics is sort of the tension between the standard, highly standardized, structured command and control of implementing systems in super high critical areas where redundancies are necessary. Think about airplanes, think about nuclear reactors, think about operating rooms and ICUs where literally downtime could cost lives, versus the much more nuanced, participatory, innovative, highly fast-paced need for informatics around discovery. And when you start to blend the culture of the hospital with the culture of the lab, you come up with that tension, which is a perfectly legitimate and fine tension. But when we now start to talk about standardized cyber infrastructure, when we talk about informatics, that is one of the things that we have to come to agreement on. And it's really a fascinating thing that we're watching evolve almost week by week now of cultures starting to come together. And I think what's helpful is also having a research background, and frankly, many of us do both of those things. So, I'm sorry, I need to go forward. So, briefly, I want to tell you about our health system and our health care. The University of Michigan is not just a really big hospital, or as of this weekend, another new huge hospital opening up. If you don't know, the Children's Hospital is opening up this weekend. We have an enormously complex and large and active medical school. We have a university health service, which, by the way, will also be going to the same electronic systems that we're talking about in the hospital. We have a school of dentistry, a school of public health, all of which are involved in much of what I'm going to be discussing. But then, even around the institution, we have many other sites that are actually participating in health care that you would normally not think of, but are both clinical health care, psychological clinics, social work clinics, even the athletic department apparently has its own sort of health care that's somewhat separate from others as well. But they're also involved in academic work, in investigation, and in teaching. I will get it. Normally I'm able to just advance here. So there are a few trends in medicine that are fundamentally shifting the lay of the land right now, and here are a few of them. Number one, the percentage of US population, seen here as the total number of people in millions on the y-axis, in years on the x-axis, who are older than 65 has reached an inflection point as the baby boomers now start to get into retirement. We are having an aging population at a rate of aging that the US has never seen before. And the implications on many things, including health, are going to be profound. And if you've heard or read in the paper that more medical schools are being built in Michigan alone, there are 3 new medical schools that are now operating in the last year and a half. 3 additional medical schools. It's actually in anticipation of the increasing need of healthcare because of that. Similarly, we actually have a decrease in the rate of births in the United States. So somewhat like Japan, already we are now entering into a US population that is older. Now that's important because as people get older, they acquire more diseases, and chronic diseases start to get worse and worse over time. And yet, when you just throw huge amounts of resources like we have had in the United States, we actually tend to modify some of those diseases. Here, the death rate for cardiovascular disease, heart disease, coronary heart disease, congestive heart diseases, and stroke have all been decreasing. And that's one of the major chronic disease burdens of the elderly. As you get older, people over 65, about 1% to 2% of people older than 65 have congestive heart failure. As that population rises, their burden gets greater. So when you throw a lot of money at it, you tend to actually make the outcomes somewhat better overall. But it's incredibly expensive, and what you then might say is, well, how expensive is that? Well, right now, we have about 130 million Americans who have some form of chronic disease. That accounts for about 70% of all the deaths, and it accounts for about 75% of our $2 trillion healthcare. So it is enormously expensive to deal with chronic diseases. And so because we spend so much money, we should be doing really, really well on outcomes and efficiencies. And not only are we not doing average, we're actually doing much worse than average. On the y-axis here, this is life expectancy as a general proxy and marker for the overall efficiency of a country's healthcare system. And on the x-axis is the amount of money per capita spent on that, on an individual. In general, you can see here, westernized countries are deviating around a certain average. And here we are, the United States is an enormous outlier to every single westernized country. So we spend about 2 times as much per capita, and yet we actually have not even average outcomes relative to other countries. And that is a major driver of a lot of policy towards what we need to do, including policies around informatics as well. We also have an issue around medical errors, which hopefully you've read and heard about, because it's really only received attention for the last 10 to maybe 15 years at the most. Now, these errors have been occurring all along, but really they've only been getting attention somewhat recently. They're about the 4th or 5th leading cause of death in the United States. Now, to be very fair, that's actually not correct. So here's an example of what would be constituted as a medical error. I, up until yesterday, ran the ICU at the CVC as the director of critical care. And you'd have a patient who is critically ill and really dying. And they would get an extra dose of a medication that didn't kill them or add to end organ injury, but we would call it out as a medication error. Well, that does fit into that rate of about 99,000 medical errors per year. So I want to put it into some perspective. That said, it's just completely unacceptable to have errors. In the airline industry, they don't say, well, we're going to have 2 or 3 airplanes crash every month. But the statistic is about a 747 a day, I believe. You know. So the order of magnitude is still pretty impressive. So because of the trends in healthcare, the trends of the aging population, the disease, the expenses that the United States goes through, and yet outcomes don't even come close to matching it, there are all sorts of movements to try to improve that. And one of them is around the delivery of care to improve quality, accountability, but also to try to change the funding mechanisms for what is still currently by far the most expensive healthcare in the world, by far. And at its core are among ideas of this idea of the medical home, an accountable care organization, or some form of integrated health system that says, you don't just come here and we do a procedure on you and you leave. We're now responsible for your care. We're responsible to make you healthy when you're sick, to keep you from getting sick. And Larry will talk a little bit about some of those kinds of things as well. But we are responsible, and shifting the idea of, please come here and we can do more stuff and get a lot more money, to we take some risk. And that's this concept of the medical home and accountable care organization, with an idea that a patient has a group of sequential layers of care, from a doctor or a clinician to a system, to a broader system to take care of primary preventive care or specialized care. And you'll hear these terms around accountable care organizations. Whether that takes off or some form of it, that's really where the country is moving. Now, everything I've mentioned isn't even remotely new. And here's just a great quote that I think spells out a great deal of why today is so interestingly important. One of our great clinicians said, "I am fain to sum up with an urgent appeal for adopting some uniform system of publishing the statistical records of hospitals, clinics, primary care providers, substitute whatever you want. There is a growing conviction that in all hospitals, even those in which are best conducted, there is a great and unnecessary waste of life. In attempting to arrive at the truth, I have applied everywhere for information, but in scarcely an instance have I been able to obtain hospital records fit for any purposes of comparison. If wisely used, these improved statistics would tell us more of the relative value of particular operations and modes of treatment than we have means of ascertaining at the present." I mean, keywords just seem to lift out of that slide of everything that in the medical side, comparative effectiveness, information versus data, comparing to one another. All of these kinds of things are exactly what we are doing right now, and you'll see in just a minute why these are so important. And these were said way over 150 years ago by Florence Nightingale. So there is nothing new, even remotely, about what we're doing right now. This is not even in the same ballpark as new. But there is an enormous revolution happening because it's actually starting to happen. Her needs at the time could not be done. Even if people were all on board, they didn't have the information systems to do it. And now we do. So what's happening to do that? Well, one of them is to adopt electronic medical records. And where are we in the United States? Well, we are really not there. This is around right now. It's a little bit old, but it's still relatively new, the year 2010. And this is the percent of, sorry, this doesn't seem to be, the percent of physicians who in their ambulatory clinic offices have an electronic medical record. And it's about 50% at best have anything. That even includes just a schedule or record-keeping system. And about maybe 11 to 12% have something that you would want, which is a fully integrated electronic healthcare record in ambulatory care. So if you go see your private doctor in their clinic or a nurse practitioner, chances are, flip a coin, they'll still be working on paper today, like Florence Nightingale lamented in 1863. How about in the hospitals? This is a measure of the sophistication of highly integrated electronic systems from 0 to 7, 7 being the most integrated. I write an order. If you don't get it done, you get a reminder, I get a reminder. There's a portal that you could log on to, all sorts of integration of documentation, clinical decision support, the things that you would want us to be doing. And about 1% of US hospitals are there right now. 1%. And way over 50% of the hospitals are essentially still using transactional systems that were really the only thing available in the late 80s and early 90s. So from the ambulatory care side, from the hospital side, at best, we're maybe about 50%. But that's changing very, very quickly. One of the reasons it's changing is that those places that have those sophisticated systems are demonstrating much better outcomes. One of them is the ability to do orders in an electronic system. You can read the orders. You can be reminded about the orders. The data can come back to multiple people because it's all digital as opposed to on paper. And here's an example of using what's called CPOE, Computer Provider Order Entry, and to use some basic forms of decision support. Hey, you just wrote to give me 1,000 milligrams of morphine when you really should have just given me 10. 100-time overdose. In fact, when we went up on our CPOE system at Michigan, one of the errors that occurred was that someone wrote for 100 milligrams of lorazepam, which is a sedative. And it was only detected because the nurse who was trying to take the dozens of vials out of the system to draw up 100 milligrams realized there is something wrong here with that order. You would think that had been brought up. But again, those things still happen. We talk about 10x errors, you know, that extra 0. And that goes from what you should get to what could kill you. Now, we have multiple redundant systems to avoid it. But those things should just never, ever happen. They should be engineered out. You, I would imagine, might say, well, why could they even write that 1,000? Right? Because that's what I would say. Why even allow for that kind of medication to even have it there? And those are the kinds of things that over time start to just get engineered out. You simply can't even write for an overdose. So when you do that kind of alerting, you can see the number of orders where there is a problem, where you've exceeded a maximum dose, goes down significantly and then sustains itself. Because really, you're having a computer, as Brian so properly said, we're having information overload. You shouldn't expect me to try to remember that for the hundreds of orders I and clinicians write a day. You want the system to take care of that. An airplane can't go forward if its flaps are deployed for landing. It just won't happen. And that's because airplanes crashed when they tried to take off with their flaps up in the landing position. They just engineered that out. And we're still in the process in electronic records doing that. Yet, it still can happen. Here's an example in our own institution where a patient had 1, 2, 3, 4, 5 potent opiates, all active orders running at once. And we've done that on paper all the time. And the reason we sometimes do it is, I don't know what you're going to need, so I'm going to write 5 different medications, or I'm going to try one. If that doesn't work, I'll write another. I'll forget to DC or discontinue the previous one. And then a really good nurse will be able to say, well, oxycodone worked better than the fentanyl patch. I'll try that right now, and you get good pain relief. The downside, of course, is you could start getting 5 different narcotics, and you fall asleep on the floor, and you die. And that has happened. And what we've done now, have engineered so that simply can't happen now. This is a slide from 4 years ago. That can't physically be done right now. We've engineered, if you write for one of those types of opiates and you want to change it, that becomes inactive. We've engineered those away. But we're still having to kind of do that individually. We don't have these real great broad standards of how to do that. I'm trying to show you this as much to give you ideas of some of the problems we face, because perhaps you might want to work on some of those solutions. So part of what I'm trying to do is to give you some of that insight as well. Okay, so Brian talked about high tech. What is happening now that didn't happen 10 years ago is there's now money, big money, behind going to electronic medical records. And it really came out of the American Recovery and Reinvestment Act, that $750 billion to try to help the economy in 2007, 2008. And within that bill was about $29 billion, $29 billion to incentivize us, US healthcare, to adopt modern, certified electronic medical records. Not homegrown, custom things that I developed on my own and that we plug into the network and try to work it out like we've been doing for the last 20 years, but now truly modern, certified, standardized approaches. The Office of the National Coordinator, which is a part of Health and Human Services, sets out the standards for what constitutes a modern electronic healthcare record, the things that it should be able to do, like that ordering system that I mentioned. And it's tied by this act to the money to CMS to pay if you do those things. For example, our health system could get about $60 million if we do this properly, and will be penalized over $100 million in the next 8 to 10 years if we don't do this. Turns out we actually already are fully electronic and have been, but we've been doing it through a lot of customized systems that are all attached together. We have to do all of this in a very fast phase, although the stage 2 meaningful use literally yesterday got pushed back to 214, so I didn't even have time to change my slide, but we have to be doing this over the next 5 to 6 years. And just as a list of some of these ideas, what we're talking about with these systems, electronic orders, checking allergies with drugs, being able to prescribe medications electronically, having your problems and issues in structured text so that you can write rules to that. It can be populating registries. It can match up to the genomic, metabolomic, metabolic data, things like that, so that other consumers can use these data now in much more innovative ways. Among the problems is that one of the things we have to do is to be able to talk. University of Michigan has to be able to talk to St. Joseph's Hospital seamlessly. Well, they're our competition. And so's Cleveland Clinic, and so's Western Michigan. We don't want to talk to them because they're our competition. We want the cases. We want the revenue. Of course, that's an exaggeration and a cynical view, but it's not entirely wrong. And yet, from the patient's perspective, from your perspective, from my perspective as a patient or consumer, I don't want you to not be able to talk to each other. I want you guys to know exactly what happened here to happen there. And so the infrastructure, the networking to have that, and the standards around what the data have to look like and how they transmit are being worked out and are part of those expectations from the Office of the National Coordinator. So although we can build our electronic system, part of what we have to do now is to attach ourselves to a network much like the interstate system in the 60s was for transportation. We have to develop incredibly detailed and robust reports at the individual practitioner level of things that I do versus Larry does versus others do. We get evaluated on it. We can be the change management and try to change our behaviors in these sorts of ways. And yet we have to do this, and why we're talking to you and why Brian, ourselves, others all work together, is that we really have to do this within the context of we are a fundamentally academic, research-oriented health system. We are not a standalone clinic. We are integrated deeply with the academic environment in the University of Michigan, and not just the health system academic, but as a university. And so the complexities of prioritization, resources, infrastructure to do all of this kind of work are part of the challenge of doing this at the same time. So let me finish with this. This is what we're doing at the health system. This is a highly simplified view of our electronic environment on the clinical side. We have more than 500 separate applications, all that have to talk to each other, all that feed into common clinical data repositories. This system here, our revenue system, is a mainframe computer that uses COBOL. We can't find people to even update it anymore. I mean, it's COBOL, right? Okay. But that's where over that's where over $2 billion of revenue flows through that system that's based on a COBOL mainframe. Where we're moving to is this, a much, much more unified system using a software from Epic Corporation out of Madison, Wisconsin, that is a modern electronic medical record. And that's going to take us about 8 years if we're lucky. Right now, we're about to change out our entire business systems in February. entire scheduling, registration, and billing systems. So that COBOL, that's going away. And then we start to go to the ED, and entire ambulatory clinics go live with the new system in August. And then we go to inpatient, ORs, and specialty areas as well. But we also have to be doing other things. We have to be attending to other needs that we have. For example, the age of thinking about what telemedicine could look like in 1924. And just as an aside, because Brian's here, I showed this at a talk the other day, Brian. I've been using the slide for about 1.5 years now. Brian saw the slide, and in my office shows up a hard copy of this journal that Brian Athey found for me at a flea market. So I have this actual journal, but one thing that came out of it, we learned something is, so this looks like telemedicine, that's pretty cool. This is a prescription getting printed out. So it's not just telemedicine, it's e-prescribing all being envisioned in 1924. Well, we're there right now. The ability to do telemedicine, remote care. I've actually done critical care via monitors through EICUs. We're actually up and able to do those things right now. But we also, as Brian said, we have to be linking these phenotypic outcome quality data to all of that innovative, highly non-standardized, difficult to get, and did you see the New York Times this morning about DNA sequencing in China? That the rate-limiting step now is going to be networking and bandwidth to transmit these enormous amounts of data. Well, we have to be doing all of that work at the same time. And when you look at what seems to be a relatively simple healthcare system, clinical, to data warehouses for research purposes, it rapidly becomes very, very complex. And then finally, I'll end with this, is that although I've been talking about this line, this line, and this line, and this line, we have all of these other projects coming down the road. Boom, 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 boom. We're in a phase of transformation that is simply orders of magnitude different than we've ever had in our healthcare system at Michigan, but this is also true around the country. And the main driver of this is that slide I showed you about the incentive and the penalty money. There's also billing issues, ICD-10 that has to change. And so we're going to be going through an enormous amount of fundamental change for the next 5 to 10 years that is truly revolutionary, which means also there are enormous opportunities for investigation, study, and innovation along the way. So that was a whirlwind overview, but I hope that was helpful to you all. Larry?
Thank you, Andrew.
Thank you. Do you need this?
I'm just going to be up here, so I probably won't. Thank you. Is that gonna work? Great. So my name's Larry Ahn. I'm the director here for the Center for Health Communications Research. So we spend our time thinking about how do we put together messages that are meaningful for patients. And so Brian showed we'll call it the omics sandwich, so to speak, sandwich slide. And Andrew talked about the amazing changes that are happening in terms of healthcare systems. And what we think about is, what are the challenges in terms of communicating around these issues? What are those communication challenges in this new omic era for patients? How are we going to communicate results of these new tests to patients? Will the public or patients understand the information they're getting? How will the new information be used to actually influence treatment decision-making? And how will this new information influence important health behaviors and lifestyle choices that people make? So this is what we spend our time sort of thinking about. And shall I say, with all the changes happening in the information landscape, we have a lot to think about. You could say, well, the omic era is already here, right? Who's heard of 23andMe or seen those sites? So I just went on their site. You can, for a couple $100, get your DNA sequenced, and they will provide you a report that gives you your risk, your own risk compared to the average risk of, I think it was up to 250 or so health conditions right now. Now, we can talk a lot about, so what do people actually do with this information is understandable, and we can drill down into some of those issues. But all is to say, the omic-ish era probably has already started, and many corporations and businesses aren't going to wait for us to get it right, so to speak. But it's really important to sort of understand what is going on in this field. The way that we approach it is with the notion of tailoring or personalization of information as well as all the other aspects of care. So when we talk about tailoring, we talk about a process that involves assessment of individual characteristics and behaviors, algorithms that are used use that data to generate important and relevant messages for people, and then to provide that in a clear and vivid format. And so how this would be implemented, for example, is that we would have a message library with a range of different messages for people with different sorts of demographic characteristics, readiness to change, or different attitudes about benefits or barriers to change, or different sorts of plans that might work for an individual. We would do assessments to understand for that specific individual what are the characteristics that are relevant for them, and then we would stitch together what we call a tailored message where all this comes together for that specific individual. We can talk about that at some length later if you want about how we actually do that. But where it's most relevant here relative to this omic area is how is health communications going to interact or work in an area of personalized medicine? And so what I wanted to do is just talk about a couple important topic areas and show some of the work we've been doing in each of those areas that I think you might want to think about or we could think about in terms of sort of approaching these areas. And the areas are health literacy, numeracy, the understanding of numbers, clinical decision support that Andrew and Brian both mentioned, the concept of shared decision making and the involvement of patients in making decisions, something I'll call conversational support because as Brian is fine, I don't know, sometimes this happens when my wife and I are trying to schedule the week, right? You can only keep 5 things in your head at each time, but we have about 30 things. So how do you create an environment where people can have productive conversations? And we're trying to create some digital environments where people can have those kind of conversations, and we can talk about that. Yep. And we can look at that. And then the other, which is really important, as we start to learn more and more about people's biology, how do we support their autonomy and decision-making so that fatalism doesn't develop in terms of their approach to diseases and conditions? So those are just some highlight areas that I guess I picked to talk to you all about here today. So first, in terms of health literacy, I think is that a term that's familiar to people in the audience or no? So there's the general notion of literacy, can people read? And then is can they read and understand information about health? And at a population level, what you'll know is about 40% of the US population has some problem with health literacy where they'll need help understanding medical instructions, pill instructions, or ask for somebody to help them read the information they get from the clinic or the pharmacy. What we've done to start to, a project we've done where we're trying to help in this area is around the issue of a biorepository DNA biolibrary consent process. This is a major initiative at the health system. I think the first informed consent for giving your DNA into the biolibrary was about 20 pages long that people were being asked to read and understand. And what we've done, actually Blake Russler and Nick Stenek have done, is they've worked with the IRB and we've worked with them around the notion of reframing a biorepository project as a biolibrary project. It's really a concept which we think people understand a little bit better, the notion that there is a DNA repository, but really thinking of it as a library, that people enter their books into the library, that researchers are able to check out the books and read it and learn things about health. And then we've tried to develop, using plain language, a simple pamphlet and a one-page informed consent, which we think will dramatically improve our ability to actually develop this resource for the institution. And of course, another approach to dealing with health literacy issues is not to rely on the written word. And this is a project we did with Christine Joseph at Henry Ford Health System. The target population was actually inner-city youth with asthma, and we were trying to put together a program that helped them manage their asthma better. And this is an example of part of the information we put together in that program, which was, did a randomized trial, found to be incredibly successful, and now we're in the process of disseminating to various states in the United States, including a couple of programs right now in rural Georgia and the South. Let's see if this plays.
It's your favorite Puff City DJ, Puff Man!
Are you trying to do this all on your own?
This is what makes up dust. Bam!
Many of professional athletes have asthma. They've learned to keep their asthma under control.
I bet you wish you had that money you spend on cigarettes.
For real.
Are you packing your rescue inhaler?
And I don't have anywhere to put it.
Is it that big? As long as you packing that inhaler, you can roll with the big dog. Puff Man out.
So that's just an example of some of the work we put together. That was about 30 seconds. And if you paid attention along the way, we packed in many of the important things about the etiology of asthma, causative factors, management factors, and sort of motivational factors for wanting to manage your asthma better. And these are things that we try to integrate into all of our programs that we develop.
Larry, I just wanted to say, when Dr. Emanuel and others went through with HITAC and the administration and tried to see where we could get the biggest bang for the buck, it was a lot of this kind of stuff. You know, this is where the big money is being spent on these chronic diseases. You know, in informing folks and getting people engaged in their health care has got to be the biggest part of the solution for chronic disease.
We think there's a lot of challenges and opportunities. That's probably the best way to say it. We definitely think there is. There's definitely a lot to be gained.
Yeah.
I want to introduce the concept of numeracy to you here. I don't know, are people familiar with that term at all? So it's basically the notion is, do people understand numbers? And if you think about the types of conversations we have in healthcare, it's vitally important that people understand what we're talking about when we say they have this percent or that percent benefit from this disease or this percent risk of a serious consequence. And what we find, unfortunately, is large portions of the US population, 30, 40% also, will have a lot of difficulty understanding basic numbers, being able to say, you know, is a 1 in 10 chance of something bigger than a 1 in 100 chance of having something? And so we have a group here, it's led by Angie Fagerlund now and Brian Zygmunt Fisher, that works very hard at trying to understand what's the best way to try to communicate information about numbers to individuals. And so they've done a lot of work in terms of looking at different graphical formats for doing that. Bar graphs that would show what is the decreased risk of needing surgery related to taking a medication, or what is the risk of certain side effects. They've looked at using bar graphs, pie charts, something called clock graphs, which are pie charts with values labeled, something called pictographs, which is the graph represents 100 individuals and shows what happens to those individuals, both in terms of the reduced risk of problems and increased risk of potential side effects. And they look at something called gist and verbatim knowledge. Gist knowledge is what you expect. Do they get the general point? And verbatim knowledge, do they understand the specific numbers? And what they found overall is that the pictograph format, the one with the multiple boxes, seems to be the most effective strategy in terms of communicating around both gist and verbatim knowledge. And that's vitally important as we design these clinical decision support tools and patient information materials to really do it in a way that people understand the information that they're getting. You know, we've also looked at how to present information about risk. The tendency really is to present information about the total risk. They would say, okay, so if you're a woman, you're considering whether or not to take tamoxifen after being treated initially for breast cancer, the risk of cataracts developing is 2.9%. Okay? But really, that's the total risk for women taking that. What's the incremental risk? What's actually the added risk that comes from taking tamoxifen? And it's really much more important to highlight that incremental risk than to talk about the total risk. And so this is the approach that Angie developed, and that shows that, you know, cataracts make it hard for women to see, so you have to explain it. Among 100 women your age who take tamoxifen, you know, the additional risk is not 2.9%, but 0.4%. In terms of the absolute risk of developing cataracts. So it's really pulling out the difference between total and incremental risk is a really important approach in communication. The last point I want to make about communication is less more. And here's an example of typical feedback both clinicians and patients might see when they're trying to make decisions about, should I have chemotherapy after I've had surgery for breast cancer, right? So this is a program, Adjuvant Online. It ties into epidemiologic databases and shows people information about, you know, of 100 women, how many will be alive, how many will be dead from something other than cancer, how many will die with some other cancer. So it's how many will be alive in 10 years, how many will die because of the cancer, and how many will die due to some other cause. And what you see here is if you have no therapy, hormonal therapy, chemotherapy, or combined therapy. And this is the standard format that you see. The problem with this format is most of the time women don't have to choose between 4 options. Usually, if it's a receptor-positive tumor, they're already on hormonal therapy. So you don't need to have that as a separate choice, so to speak. The really choice is coming down to them. Is it chemotherapy or no chemotherapy. And so if you do something so simple as present, the original format, here's your 4 options and choices, versus a simple format of here's the 2 options that we think is most relevant to you, and what they see there in that little yellow bar, that's the incremental benefit of chemotherapy. And I think they can see that here, but it's kind of hard. Oops, it's going the wrong way. It's kind of hard to find the right bar here to look at, if you know what I mean. So there's information, and then if you present it using a pictograph format, it's those 2 yellow boxes there right next to the red. That's the incremental benefit of chemotherapy. And what you find is, maybe not surprisingly, that women's understanding of both gist and verbatim knowledge is much improved when you focus on the choice that's most relevant for them. And this is going to seems simple, but vitally important when we think about how we're going to implement these sorts of decision support tools.
How we're going to just inform folks of their choices and taking that omic sandwich and putting it into something like this. Larry, watching. Got a lot of work to do.
Yeah, so I want to jump now just a little bit into the area of clinical decision support. And it's really interesting because as we started to dabble into this project is Jeremy Sussman's project. He works at the VA and is in general medicine. It's a notion of, there's guidelines for treating hypertension, there's guidelines for treating cholesterol, there's guidelines about when to take aspirin, and those are going to be modified by sort of clinical factors and eventually omic factors. But what are you actually trying to treat, right? What you're actually trying to do is you're trying to treat cardiovascular disease. So what if instead of treating each measurable condition one at a time with its own set of rules, we combined all those rules and tried to reduce somebody's risk of cardiovascular disease. And this is where the slide that Brian showed, showing how many factors can a person keep in their mind at the same time, becomes really relevant. And so what we've done in this tool, it's in prototyping stages right now, is we've built a tool that takes into account their clinical risk factors, the current medications they're on, and makes a personalized recommendation about what sort of medication changes are going to optimally reduce this person's risk of cardiovascular disease, right? And what we've shown, and from his modeling work's done, that if you implement a personalized approach like this that really is trying to reduce the risk of the end condition rather than manage all of the most easily measurable and modifiable risk factors, we can double our efficiency of treatment. And that means we can get the same amount of overall benefit with half the number of prescriptions, or we can prescribe the same number of medications and double the population benefit and individual benefit of our approaches. So this is just an example of some preliminary work we're doing in the area of clinical decision support, tailoring, and personalization. And right now, there's no omic factors in this equation, but I think as they are identified, they just become additional elements of these equations. And that's why I share it with you here. And then people can do drill downs and get specific benefits, all that good stuff about how do you actually present risk. We try to adhere to that as well in these tools. Let's talk about shared decision making for a moment, because many times, it's the clinician who will decide and make a recommendation, but many times it's a decision where there's not a clear right or wrong answer, and we want to try to understand how do we help educate patients to participate in that kind of decision. This is an example of a site we did with Sophia Mariver and Scott Roberts. The goal was to develop a site for women who were coming in to the... All right. I'm not distracted. I really do want to be here. I'm joking. My calendar just drives me along every day. Okay, here we go. All right, so the population was women coming to the breast and ovarian cancer clinic, and what we did is built an interactive experience, originally on computers, now web-based, to help them learn about the basics of breast cancer genetics and whether or not they would proceed on to get screening for additional genetic risk factors for breast cancer. So there was a large component of it that had to do with basically helping people understand what is DNA, how is that related to their risk, that I thought was really important as well. What we're also finding is that I think these omic factors will be really interesting, but how do we put them in context for patients relative to the other things that are important to them? And this is an example where we try to address the issue of preferences and trade-offs. We don't have omic factors in this project per se, but I wanted to share this as a methodology approach to thinking about how to approach this issue. And so it's really the point that if we want to provide personalized patient-centered care, we want to provide care that's respectful and responsive to individual patient preferences, needs, and values, and that those are considered when making treatment decisions. The challenge is, of course, that it's very hard for people to assess or identify their preferences. If you ask people what's important to them, they will say a lot of things are important to them, and the thing that's very hard, who has teenagers? Teenagers, anyone? Very hard to have a teenager prioritize of those things, all of which are vital to them and their existence, which ones are the most important. But those are the things that people have to do in terms of making treatment decisions. And so what we've done is we've adapted a methodology from market research called conjoint analysis. And this is a method that's been used that when people are developing cars or soda or food products to try to understand what are the characteristics of products that people value. This would be an example of very simplistic conjoint analysis around auto design. You know, how important is color? How about size or style? How about mileage? If you ask people these questions directly, maybe they've been trained to learn to say that mileage is important to them, and they will say mileage is important to them. And then you'll go design a high mileage sedan. But if you give people actually discrete choices where you offer them different combinations of these things, what you find is they actually choose the red SUV. And by giving people a series of these choices, you can actually elicit from them their actual preferences. And what we've done is developed or used that sort of methodology around the prostate cancer decision aid, where we try to give basic information about prostate cancer, help them understand what the disease is, make sure they understand some of the basics in terms of the risks of death from prostate cancer. And then we go through a sort of a conjoint analysis exercise where they will tell us through their hypothetical choices whether it's really important to get the cancer out of their body. How important is sexual dysfunction? How important is urinary incontinence or bowel problems or the likelihood and length of treatment of recovery? So these are things that we elicit from them, and they'll create a personalized list through choosing these hypothetical scenarios of what their values might be. And then we use that to help guide a conversation with them about treatment choices. Last one is a project we're doing with Michelle Heisler. Then I'll stop because I'm sort of short on time. A project with Michelle Heisler. This is actually an effort to disseminate AHRQ's consumer guidelines around diabetes medications to underserved populations. This is a project, it's happening with the community clinic in Detroit, the Chaz Clinic. And what we're trying to do here is to create an iPad application where people can go, and it's going to be personalized or tailored and help give them sort of the background information that they need to have an informed conversation about diabetes and medication choices. So just the things to point out in terms of design, which we think is really important. We design it separately for and are sensitive to race and ethnicity. We build in many cultural factors into design. An individual's session would be populated with their own clinical information. There's interactive exercises where they can show how their choices around diabetes control influences their risk of complications from diabetes. And then we put together stories of characters like them that are facing similar issues for them to read and go over together. In the interest of time, I'm going to stop there. We also do some autonomy support work trying to understand how do we better support patients' sense of free will as they're learning information about their DNA, which I think is a really critical and important area. Okay, so just really quick, you know, based on your, what if you got the message, based on your DNA, you have a 30% chance of developing diabetes. People go down different paths when they get that information. Some people say, well, I really need to exercise and eat better. Other people say, well, I guess there really isn't that much that I can do. And so what we've started to do in our work is to understand what is it that influences people's approach to this type of information, and how can we build and support people's autonomy in their decision making. This work is being done by Ken Resnikow in the School of Public Health. It's based on a specific theory in health behavior called self-determination theory, which argues that people have essential needs for feeling of competence, autonomy, and relatedness to others, and how do we support that? And it leads us to develop these alternative types of advice or messages called push or pull, where push messages are ones that basically are telling people what they should do or how they should do things, whereas pull messages are trying to help them generate or come up with these types of things on their own. And in some early work around nutrition and fruit and vegetable intake, we can show that if we present information to people with a high need for autonomy in an autonomy-supported fashion, they will actually be more likely to increase their fruit and vegetable intake than others. So that's just a quick overview of some of the communication challenges that we see in the sort of new era of personalized medicine and some of our early work to try to address those areas. So.
Thanks, Larry. Why don't you just stay
up there?
Yeah, we're going to have some questions. Oh, yeah. She wants me to grab this mic.
Okay.
And then you can stay up there. Yeah, a couple things. So, you know, just doing the gap analysis. Yeah, okay. Let's see. One of the things that we didn't talk about, and it wasn't in Andrew's slide, and, you know, it's related to this idea of the patient portal. I wonder if you can say something about that.
So I think the patient portal is going to be a vitally important piece of real estate, digital real estate, moving forward. I would actually think, we've been thinking of it sort of more broadly. The experience with patient portals, most places they've been implemented, is that it is a self-selected minority of patients that actually go use it. And perhaps those that need it the most, a patient portal, I should define my terms, is a way for the patient to access their health records, request appointments, refill medications, and sort of manage certain aspects of their health care. Unfortunately, what I've read of sort of early implementation of those things is that it's a self-selected, sort of the worried well that are the ones that engage with the portal the most, as opposed to those who might need it the most. So what we're actually thinking of doing in terms of our approach to the portal is we're adapting a broader view of thinking of more proactive programs that would do outreach via people's cell phones, mobile devices, other things, and tie that information back into the portal as hopefully to generate a site that has value for patients. So I think it's vitally important, but I think it needs to be a proactive thing, not a place for the worried well to go.
I think that's great. It leads me to my next question for you, which is related to tablets and phones and mobile devices and, you know, doing more home monitoring, and how does that fit into this continuum? Right.
Well, I think it's absolutely important, and that's where, particularly with, you know, we could tap into the expertise in the audience. We really view ourselves as a group that has expertise in the creation of meaningful messages. We need information to then be processed to help us understand what messages to write. Most of our information has come from self-reported answers to survey questions, but the world is wide open in terms of the types of information that can be collected from home monitors, physiologic monitors, social networks, or other sorts of things. So that's particularly, you know, an area that we're interested in developing additional collaborations.
Hello?
Hard question. You know, we heard this morning about an elaborate project to instrument the ocean and to actually steer instrumentation by closing loops. The auto industry is actually making reasonably good progress on doing that for automobiles. So where are we with respect to personalized medicine and kind of having real-time feedback from the human and then monitoring and processing that data and doing maybe, you know, interventions and so forth? I mean, and what are the barriers to doing more there? For example, I think there are things out now where you could read your blood pressure into your iPhone. Your iPhone could send it off to some database, and something over across the street here could be monitoring that and triggering intervention. But are there other billing barriers, compliance barriers? I mean, why can't we be doing that routinely now?
I'll take a first stab at it, then I think, Brian, you'll probably be able to answer better. One thing, it hasn't stopped the research per se, but does become a challenge in terms of implementation, is the system of financing and reimbursement currently does not support these types of activities, right? So if you're going to put these things in place, and we still think they have value, it's really important to understand what's the financial model for getting those implemented and carried out over time. I would argue you can do it And because these types of monitors can actually save in terms of expensive person power. So you can show that. But I think the other way of answering your question, there probably is a need for broader financial reform. And some of the work that Andrew talked about in terms of accountable care organizations, I think are going to move in that direction. In terms of answering some of your other questions, we'll start sort of macro and go more minor. So there are all the devices that you can see, hear, and hold, right? Scales, glucometers, blood pressure measures, those are all out there. My basic approach to those is they're all good, but they can all be made better. They refer to these devices as smart, but I don't think they're really smart right now, because what they do is they beep at you. Last time I was like needing to be motivated, a beep was not particularly motivating to me. So you can imagine a pill box that might beep if you don't take your medications. What we'd like to do is to have that pill box be able to tie into intelligent messaging that could remind you of what might your core values be, why you might want to manage your diabetes better, and give those types of reinforcement messages instead of just beeping at you. So it's...
But we can think beyond that.
Okay.
Think about implantable things.
Right. And
yeah, and measuring the health of populations,
right.
which is one of the goals of going back to
right.
Andrew's slide and meaningful use.
Right.
Yes, I mean, in 2015, we really have to have reports out to the government, CMS, and other
right.
government agencies on how the health of our population is improving based on the meaningful use of the electronic health
right.
records. It's written in the legislation. So part of what
I
we're
guess
doing.
The bottom line question is all this that we're doing across the street here, all these hundreds of millions we're spending,
right.
anticipating the kind of real-time monitoring.
I think that we are.
Their day-to-day life.
Yeah, the two that I know about, and then Brian, please fill in the gaps. Is Dr. Najafi, right? Dr. Najafi and the WIMS Institute, and then Mark Burns. Is it Mark Burns, the chemical engineering? They're doing a lot of work with microsensors, and they at least the Micro Sensing Institute. There's sensors for inside the eye around glaucoma. I think people are developing sensors that actually implant inside tumors to measure initial response to therapy and let tailoring of chemotherapy. So I think people are developing in those areas. If that's sort of the direction you were thinking to go?
There's no question about it. It's just, you know, the talk this morning.
My question is partly, yeah, I know Mark Burns' work and I know all the nanotechnology.
But what about the sensor net?
The question is, are there these barriers, like we don't know how to charge for it, or we don't know how to handle it within HIPAA, or we don't have the right network connectivity?
And there is a movement out there. There's this mhealthy.org, if you check that one out. Deborah Estrin, who you probably know well from UCLA, and Ida Sim up at UCSF, who's a MD, PhD medical informatician, have joined forces and created this not-for-profit to be a clearinghouse of, you know, frankly, apps that could be put on these mobile devices that can seed up some of these sensor networks. And we're seeing a great deal of success in something called the PTSD Coach, which is an app that can be implemented on a mobile phone in folks who suffer from post-traumatic stress disorder, and their families can have this mobile app and could feed into the VA and the DoD electronic health record systems and collect a vision across the spectrum of PTSD sufferers, both you know, people who are still in the service and people from the National Guard Reserve that came in who are back in the community, and these kinds of things are taking off. So that's just one example. But I would say, and this is one thing, there was a call, HIPAA, you mentioned it, but you'll notice we didn't say it, so there's something wrong there. I mean, that's a biggie. So I don't want to even go there. But one thing with personalized medicine and healthcare, and I'd love to hear what Larry has to say about this. You mentioned 23andMe, but that's not the only one. There are several, you know, it's not going to be that we at the health system or any one hospital are going to have many of our own tests. There are going to be tests and advice and all kinds of things coming at us from all over. So the question is, the other thing that we didn't mention is personalized health record. That word wasn't mentioned.
Right.
So you can see that we're dealing with the whole panorama of change.
Yeah, so I think that's, You know, this debate, I just came back from Honduras over Thanksgiving, and there's a very interesting debate going on as they try to modernize their healthcare system. Should they try to build electronic health records that are clinic-based, or should they really build it around the patient in terms of personal health records? And so there's some very interesting conversations, particularly in the developing world, about what are the best strategies for trying to get, you know, who's the center of the health information nexus, so to speak.
Okay, yeah. Chris?
So I think this is a little bit springboarding off of some of the discussions.
Here you go. Thank you.
Sure. So some of what you mentioned was, I guess my question is essentially, if you build it, will they come? We know, all the people here know we're going to get hit with this volume of information, and this information is potentially extraordinarily useful. But for individuals with different cultural backgrounds and different demographic values,
Right.
will they actually adopt this new wave of technology and information? And if they do, how can we help them? I mean, and I know that's your whole thing, but if we're seeing a diversity of services like 23andMe, how are they going to make an informed choice?
So I think that's a really big question. I'm not sure I have all the answers to that. What we do try to do in terms of, I think if anything, it will come to the issue of where is trust generated, right? So a lot of what you're talking about is who trusts what and why. And what we're finding, and this is from like Health Information National Trend Survey, other sorts of things, there was this thought way back when that as more and more health information became available, as people's trust in their physicians would go down. And in fact, I think we're seeing the opposite, as people are gaining more and more access to different kinds of health information. Rightly or wrongly, their trust in their physician is going up, right? I think what we can try to do is build tools that can help, you know, help guide or inform these conversations to help people find the information out there that's most relevant for them. I do think, particularly for a portion of the population that's going to be the least advantaged and have the greatest needs, they won't come unless we build programs that are able to go out to them, that are going to reach them through their phones, that are going to reach them in other ways that they sort of value. And then if we're going to do that, we have to demonstrate value added. They have to perceive the value of what they're doing. Otherwise, we might get them once, but they're not going to stay with any sort of program.
Another question back
This is not so much a question as a comment.
Okay.
My name's Patricia Anderson. I'm the Emerging Technologies Librarian for the Health Sciences.
Oh, we have to meet.
We have to talk.
Okay.
There's a huge community working on the area of mHealth apps, I'm sorry, mobile health apps, the healthcare social media community. I'm deeply engaged in those communities. There's work going on in the library system to support both the healthcare social media activities and the health outreach, health literacy, plain language movements on campus. There's an initiative from NLM to support the information prescription for those patients who need the extra help and support of directing them to a librarian who will hold their hand and talk them through it personally.
Sure.
And going beyond, there's
Absolutely.
There's all these resources to tap into to
Right.
support the type of work that you're talking about. I'm working with the Mayo Clinic Center for Social Media. I'm on their board. There's a team I'm working with, a couple of different teams I'm working with on campus who are doing research on social media adoption for healthcare outreach and interventions. There's a huge amount of stuff going on that we could be sharing on campus.
Great. Absolutely.
I want to encourage everybody to take a look at one site along these lines. Another area emerging is the patient advocacy community, social network. Just take a look at Patients Like Me as a link, little homework assignment. It is an absolutely fascinating community that's evolved around peer-to-peer. About 140,000 very active members around neurodegenerative diseases. There was a movie made out of the founding of this incredible, frankly, story. I've had a chance to meet those guys.
Did you see the research that Mayo just did based out of that? Where they found an online patient care community for an extremely rare disease. At that time, the maximum population in a clinical trial on that disease was about 40. And by working through the social network, they were able to do a clinical trial remotely through distance connections of over 80 for this rare disease, doubled the size of the previous clinical trial. There's some amazing stuff going on.
It's a game changer. Like in cancer, you know, you'd think cancer research is a big deal. We have trouble. We don't even get up to 5% of our patients coming into the clinics are participating in the research studies. Over half of the clinical research trials that we start don't accrue enough patients to go through. And you know, this is a new way of that we can actually, you know, do a lot of good and support a lot of patients, and they share information. It's fantastic. Anything else? Any other questions? Andy? Yeah.
So as you look at where the center of all this is, how much, you know, there's a lot of concern in the general population about as it's become institutionalized, sort of personal loss of the health record, you know, particularly for privacy issues. I'm just sort of curious how the state of current privacy legislation is encouraging or discouraging in terms of people feeling willing to have this information kept centrally versus personally?
So there's a couple different ways to answer that question. I think I think the Patient Like Me site is a very interesting example to bring up when thinking about privacy issues. This is probably an oversimplification, but physicians and health system administrators are probably more concerned about privacy than patients themselves in most cases. And we are surprised at what patients are willing to share when they perceive there's a benefit. The important thing to have in building these platforms, my sense is to make sure you're absolutely transparent in terms of what is and isn't being shared, and to make sure that the patient and the individual whose information it is has that choice in terms of what information is shared. So that's relative to those sorts of things. Anyways, that's my first answer, if that partially addresses your question.
Well, it's a large degree of generation, you know, demography. You know, you can really draw a line, and the younger people are not having so much trouble sharing information as the older generation. I mean, it's really. Then there's a whole literature about, you know, identifiability and things like that. You know, just in our own little area here. And Dan gave me a call last week about Amazon's potential offering to have a HIPAA secure, you know, cloud service. And, you know, we need these kinds of things. So there's indemnification issues. There's issues of, you know, the institution and the payers and the pays, and also of course, the participants and patients. Catherine, we're getting the hook.
I just want to thank all of you. I want to thank all of you for coming today. This is the end. I wanted to give people enough time for the networking break, which happens from now until 3 o'clock. So we have about 20 minutes. There's more food out in the atrium, and Victoria Stodden, am I pronouncing it right? Oh, good. Who's right back there, will be presenting in Forum Hall starting at 3 o'clock. It will be about the reproducibility of data. And it should be a fantastic presentation, as I understand, because Dan has seen her speak before. So, and so has Brian. So,
I saw you through the TV set in the double AMC meeting.
So that session will be in Forum Hall, just down here, following the networking break, which is brought to you by Google. And following her talk will be a town hall. We encourage as many of you as possible to come attend as a way of giving us feedback about what we're doing and how the Office of Research Cyber Infrastructure can meet your needs going forward. So thank you very much again.